In the beginning, approximately 13.8 billion years ago, our universe exploded into existence from an infinitesimally small point of unimaginable density and heat. A cosmic genesis event that physicists call the Big Bang, a moment when all matter, energy, space, and time itself burst forth in an instant of creation that defies our everyday intuition and challenges the very language we use to describe reality. This theory emerged from observations made in the 1920s when astronomers discovered that distant galaxies were moving away from us, suggesting that the universe itself was expanding, a finding that when reversed backward through time points to a single origin moment from which everything we know originated. The mechanism behind this understanding rests on Einstein's theory of general relativity, which describes gravity not as a force but as a curvature of spacetime itself. And when this mathematics is applied to the entire universe as a whole, it reveals that our cosmos must have begun from a state of infinite density called a singularity, a point where the laws of physics as we understand them break down entirely and cease to have meaning. What makes the Big Bang theory so persistently compelling despite its seemingly impossible nature is that it has survived decades of rigorous testing and observation, with predictions such as the cosmic microwave background radiation, a faint afterglow of the initial explosion, being detected with extraordinary precision by successive generations of satellites and instruments, each confirmation adding weight to a narrative that would otherwise strain credibility beyond breaking point. We have normalized the idea that time itself had a beginning, that there was no before, that asking what came before the Big Bang is a category error equivalent to asking what is north of the North Pole. And this normalization reflects how thoroughly empirical evidence can reshape human understanding, transforming the seemingly unthinkable into accepted knowledge that structures how we comprehend existence itself. Imagine a future so distant that it exists beyond human comprehension, a moment when the universe has expanded so infinitely that all stars have burned out, all black holes have evaporated through Hawking radiation, and every atom has decayed into its most fundamental particles scattered across an incomprehensibly vast void. This is the heat death of the universe, one of the most profound and melancholic theories about the ultimate fate of existence itself. According to the second law of thermodynamics, entropy always increases in a closed system, meaning that energy becomes increasingly dispersed and unavailable for useful work, and the universe itself is the ultimate closed system. As time progresses eternally into the future, all usable energy will be exhausted, all temperature differences will equilibrate, and the cosmos will reach a state of maximum entropy where no stars shine, no planets orbit, and no life can possibly exist. The mechanism underlying this theory is fundamentally about the arrow of time and the nature of energy transformation. Every process in the universe, from nuclear fusion in stars to the beating of a human heart, requires energy gradients and temperature differences to function. When energy becomes evenly distributed throughout space with no temperature differential, no work can be extracted, and all activity ceases permanently. Yet despite the logical inevitability of this conclusion emerging directly from our most fundamental physical laws, humanity continues to build civilizations, plan futures generations ahead, and invest emotional significance in long-term projects with little acknowledgement of this ultimate cosmic endpoint. We have normalized the cognitive dissonance between knowing that everything we build will eventually be rendered meaningless by universal entropy, and our psychological need to create purpose and meaning in our present moment. Imagine the entire cosmos, every star, every galaxy, every particle of matter and energy that exists, suddenly reversing course and collapsing inward upon itself with an acceleration that grows faster and faster as time progresses, ultimately converging at a single infinitely dense point from which all existence emerged in the first place, creating a symmetrical mirror image of the Big Bang but running in complete reverse. This is the concept known as the Big Crunch, a theoretical endpoint to our universe that stands as the inverse catastrophe to its violent beginning, and it fundamentally depends upon one crucial cosmological condition: that the universe possesses sufficient mass and gravitational pull to eventually overcome the expansion that has been accelerating since the moment of creation itself. The mechanism underlying this theory rests upon the balance between two competing cosmic forces: the outward pressure of expansion driven by the initial Big Bang and the inward pull of gravity exerted by all matter throughout space. And if gravity were merely strong enough, it would gradually slow this expansion until all motion ceased, then reversed. Drawing everything back together across billions or trillions of years, until the final collision occurs in a moment of unimaginable density and temperature. What makes the Big Crunch particularly compelling as a concept is that it provides a kind of poetic symmetry to existence itself, suggesting that the universe might possess a genuine beginning and ending, bookended by singular moments of infinite conditions. Yet modern observations of cosmic acceleration through dark energy have substantially diminished the likelihood of this scenario actually occurring. Consider the universe as we understand it today, expanding outward in all directions at an accelerating rate, driven by a mysterious force known as dark energy that comprises nearly 70% of all existence. And imagine what happens if this acceleration never slows down, but instead intensifies exponentially over cosmic timescales, reaching a point where the very fabric of spacetime itself becomes stretched beyond the point of no return. This is the Big Rip, a theoretical endpoint for the universe where dark energy grows so powerful that it tears apart not merely galaxies and stars, but eventually atoms themselves, ripping apart the fundamental structure of reality in a violent, catastrophic unraveling that would occur trillions of years from now. The mechanism behind this apocalyptic scenario rests on our observations of cosmic expansion and the behavior of dark energy, which appears to have a negative pressure that counteracts gravity, pushing matter apart rather than pulling it together. And if this repulsive force increases over time according to certain mathematical models, it would eventually overcome every binding force in existence, from gravity holding galaxies together to the strong nuclear force binding quarks within atoms. The psychological weight of this theory lies in how it presents a universe not gradually fading into cold silence as previously imagined, but instead being violently dismantled by an invisible force that we barely understand, transforming the cosmos into chaos and emptiness in a manner that feels both alien and deeply unsettling to contemplate. What persists about the Big Rip despite its theoretical uncertainty is that it represents one of the most concrete possibilities we have derived from our best current measurements and mathematical frameworks, rendering it neither fantastical speculation nor certain prediction, but rather a sobering reminder that the ultimate fate of everything may depend entirely on the nature of dark energy, which remains perhaps the greatest mystery in all of modern physics. Imagine standing at the edge of an infinite timeline where every moment that has ever occurred will occur again, precisely as it happened, repeating endlessly through the cosmos without variation or deviation, a concept that has haunted philosophers and physicists for centuries with its unsettling implications about free will, meaning, and the fundamental nature of existence itself. This is the theory of eternal return, first popularized by the German philosopher Friedrich Nietzsche in the 19th century, though its roots stretch back to ancient Stoic philosophers who grappled with the cyclical nature of time and the possibility that the universe might eternally repeat itself like a cosmic loop with no beginning or true end. The mechanism underlying this theory emerges from several converging ideas. If the universe contains only a finite amount of matter and energy operating within a finite space, and if those materials follow deterministic physical laws without exception, then mathematically speaking, eventually all possible configurations of that matter must repeat, creating an inevitable eternal recurrence where identical histories unfold again and again across infinite time scales. The implications prove deeply unsettling because they suggest that you, precisely as you are now, will exist countless times throughout eternity, making identical choices, speaking identical words, and experiencing identical moments of joy and suffering with no awareness of the previous iterations, condemned to repeat the same life infinitely without memory or progress. What makes eternal return persist in philosophical discourse, despite its troubling conclusions, is precisely its refusal to offer comfort or escape, forcing us to confront whether our lives possess inherent meaning if they are predetermined to repeat identically, and whether such repetition would constitute a form of eternal imprisonment, or, as Nietzsche himself suggested, a reason to embrace and affirm existence so completely that we would willingly accept living our lives infinite times over. Imagine that this very moment, the one you are experiencing right now as you listen to these words, is not actually happening in any special way. It is simply one location in a vast four-dimensional landscape of spacetime, no more real or present than yesterday or tomorrow or 1,000 years from now. This is the essence of the block universe theory, a conception of time that emerges directly from the mathematics of Einstein's theory of relativity and challenges our most fundamental intuition about the nature of existence itself. According to this view, past, present, and future all exist simultaneously and equally in a grand block of spacetime, and the sensation that we are moving through time, that events are occurring and then ceasing to be, is merely an artifact of human consciousness, a subjective experience with no objective foundation in the structure of reality. The theory arises from a rigorous examination of relativity theory, which reveals that there is no universal present moment that divides past from future in the way our everyday experience suggests, and that different observers in different reference frames disagree fundamentally about which events are happening now, suggesting that presentness itself is not a feature of the universe, but rather a perspective-dependent illusion. What persists in our minds is the powerful conviction that we are always at the edge of existence, that the future remains undetermined and open, and that the past has somehow solidified into something fixed, while the present alone possesses reality and causal power. We continue to experience time as a river flowing in a single direction, carrying us inexorably forward, despite the fact that modern physics describes a universe in which there is no flowing, no becoming, no fundamental difference between the three dimensions of space and the one dimension of time, only a static eternal structure in which all moments, your birth, your death, every joy and sorrow you will ever feel, already exist in their appointed places, equally real, equally present, awaiting only our physical or conscious arrival at those coordinates in spacetime. In the distant future, as the universe approaches its final state of maximum entropy and heat death, something remarkable and deeply unsettling emerges from the equations of thermodynamics and statistical mechanics. The Boltzmann brain is a thought experiment that asks us to consider the spontaneous formation of conscious minds arising purely by chance from random molecular fluctuations in an otherwise empty universe. Named after the 19th century physicist Ludwig Boltzmann, this concept suggests that in an infinitely old and infinitely large universe, even the most improbable events must eventually occur, and among those events would be the random assembly of atoms into configurations capable of conscious thought. A human brain, with all its intricate neural structures and electrochemical processes, could theoretically materialize from the quantum fluctuations of empty space, fully formed and complete with all the memories and experiences necessary to perceive itself as an existing being. The mechanism behind this possibility rests upon the mathematical certainty that given enough time and space, any configuration of matter, no matter how unlikely, will eventually manifest through pure chance. In an eternally expanding universe where entropy constantly increases, the probability of any specific arrangement of particles remains eternally present, and therefore, across infinite time scales, brains could emerge spontaneously, think their singular thoughts, and then dissolve back into chaos. What makes this theory so philosophically troubling is that it undermines our assumptions about the nature of observation and reality itself. We persist in constructing civilizations, accumulating knowledge, and developing elaborate consciousness, despite the logical possibility that we might simply be temporary anomalies in a cosmic void. Random statistical fluctuations no more real or meaningful than countless other disembodied minds that have spontaneously formed and disappeared throughout eternity. Imagine a universe that does not begin with a singular explosive moment of creation, but rather exists as an eternal cycle of expansion and contraction, where what we perceive as the Big Bang is merely the rebound from a previous universe's collapse, a cosmic phenomenon so vast and fundamental that it challenges our most basic understanding of causality, time itself, and the very concept of beginning and end. The Big Bounce theory proposes that the universe operates like an infinitely elastic ball, eternally bouncing between states of expansion and contraction, where each cycle lasts trillions upon trillions of years, creating what some physicists call an oscillating or cyclic model of cosmic evolution. In this framework, the Big Bang was not truly a beginning, but rather a transition point, a moment when an ancient universe contracted under its own gravity, compressed into an unimaginably dense state, and then rebounded outward again, birthing our current era of expansion. This theory emerges from attempts to reconcile quantum gravity with cosmology, particularly through approaches like loop quantum gravity, which suggests that quantum effects at extremely small scales might prevent the universe from ever forming a true singularity or infinite density point, instead causing it to bounce and reverse before reaching such extremes. The psychological appeal of this theory lies in its resolution of one of philosophy's oldest dilemmas, the problem of causality and what could possibly exist before creation. For in a bouncing universe, there is no absolute beginning, no moment of pure nothingness requiring explanation, only an eternal cycle where cause and effect perpetually feed into themselves across billions of years. Yet despite its elegant logic and growing mathematical support from quantum gravity research, the Big Bounce remains speculative and unprovable, existing primarily in the realm of theoretical physics, where observational evidence cannot directly confirm whether our universe is truly one bounce in an infinite sequence, or whether the concept of previous universes before our own has any meaningful reality whatsoever. Conformal cyclic cosmology, proposed by mathematical physicist Roger Penrose, presents a radical reimagining of cosmic history by suggesting that the universe does not have a singular beginning or end, but rather exists as an infinite sequence of cosmic ages, each following the previous one in an eternal cycle of rebirth and expansion. In this framework, what we perceive as the Big Bang is not truly the origin of existence, but rather the infinite remote past of a previous cosmic eon, a perspective that fundamentally challenges our conventional understanding of linear time and causality. The mechanism underlying this theory rests on a sophisticated mathematical principle called conformal invariance, which allows the infinite distant future of one universe to be mathematically identical to the Big Bang of the next universe, creating a seamless transition between cosmic eons that we cannot possibly observe but can theoretically describe. What makes this concept particularly compelling is that Penrose has argued that evidence of supermassive black hole collisions from the previous eon might be detectable in the cosmic microwave background radiation as concentric circles of Hawking radiation, suggesting we might possess physical proof of this cyclical structure if we examine our skies carefully enough. The psychological appeal of conformal cyclic cosmology lies in its resolution of profound philosophical problems. It eliminates the need for an absolute origin point, removes the troubling question of what existed before the Big Bang, and replaces linear cosmic destiny with eternal recurrence and renewal. Imagine the fabric of reality itself is not as stable as we believe it to be, that the quantum vacuum upon which all existence rests exists in a state of precarious equilibrium, poised perpetually on the edge of catastrophic transformation. This is the unsettling premise of vacuum decay theory, a hypothesis emerging from quantum field theory that suggests the universe might be dwelling in a false vacuum rather than the true ground state of energy, much like a ball balanced precariously atop a hill rather than nestled safely in a valley below. According to this framework, the vacuum state we observe around us, the seemingly empty space that comprises the vast majority of the cosmos and underlies all particles and forces, may not represent the lowest possible energy configuration available to the universe. Should quantum fluctuations ever trigger a transition to a lower energy state, the consequences would be absolutely catastrophic and irreversible, as a bubble of true vacuum would begin expanding outward at the speed of light, fundamentally altering the physical constants and laws of nature itself in its path, rendering all matter, energy, and complexity impossible within the affected region. The mechanism underlying this terrifying possibility rests upon the mathematics of quantum field theory, where particle masses and interaction strengths are not eternal constants, but rather depend sensitively upon the vacuum state in which they exist, meaning that a transition to true vacuum would change these fundamental parameters so drastically that atoms could no longer hold together, stars could no longer ignite, and life as we understand it would cease to be even remotely feasible. What makes vacuum decay particularly unsettling is that we cannot definitively rule it out through observation, for such an event would announce itself only at the moment it arrives, destroying all means of warning as it propagates across the universe in an expanding sphere of transformation, and we would simply cease to exist without ever knowing it was coming. Imagine standing at the edge of everything we know, only to realize that everything we know might be just one island in an infinite archipelago of realities, each with its own physical laws, its own particles, its own history and destiny unfolding in complete isolation from ours. This is the concept of the multiverse, a theory that has emerged not from philosophical speculation alone, but from the very mathematics that underpins modern physics itself. When physicists solved the equations of quantum mechanics, they discovered that particles exist in a state of superposition, occupying multiple positions simultaneously until observed, and some interpretations suggest that every possible outcome of every quantum event actually occurs, branching reality into countless parallel universes where every decision you never made was made in another version of you. Similarly, inflation theory, which describes the explosive expansion of the early universe, suggests that the Big Bang may never have stopped. Instead, cosmic inflation continues eternally in some regions of space while ending in others, creating bubble universes that spawn from the quantum foam like bubbles rising through infinite water. The psychological appeal of the multiverse is profound because it offers a peculiar kind of comfort alongside existential vertigo. It means that somewhere, somehow, every possibility is real, every choice you regretted was taken elsewhere, every tragedy you endured was avoided in another branch of existence, and every dream you abandoned was pursued by some version of yourself in some parallel reality. We have grown so accustomed to this idea that it now permeates our entertainment, our philosophy, and our casual conversations about fate and choice, despite the fact that the multiverse remains fundamentally unobservable and perhaps entirely untestable, existing more as a mathematical consequence than as an empirically verifiable aspect of reality. At the quantum level, particles exist in states of superposition, occupying multiple possibilities simultaneously until the moment of observation collapses them into a single reality. Yet the many worlds interpretation suggests something far more profound, that no collapse occurs at all, and instead, every possible outcome of a quantum event actually happens, each unfolding in its own separate branch of reality that splits off at the moment of measurement. When a physicist conducts an experiment with a particle that could spin either up or down, the conventional view holds that the act of observation forces nature to choose. But according to this interpretation, the universe itself branches into two equally real worlds in that instant. One where the particle is up, one where it is down, and both versions of you exist to witness their respective outcomes, completely unaware of the other's existence. This framework emerged from Hugh Everett's doctoral thesis in 1957, presenting a radical challenge to the Copenhagen interpretation's requirement of wave function collapse, instead proposing that all possibilities are preserved forever across parallel realities that diverge exponentially with each quantum event. The mechanism underlying this theory rests on a profound observation about the nature of quantum mechanics itself. The mathematics that governs subatomic particles contains no special instruction for collapse, no rule that says reality must choose, suggesting that perhaps the collapse is merely a convenient fiction we impose to make sense of our singular perspective rather than a genuine feature of nature. What persists despite its extraordinary implications is a certain logical elegance that resonates with physicists. If the mathematics works perfectly without requiring collapse, why introduce it? And if we accept that all possibilities are real, then the branching of worlds becomes not an aberration, but a necessary consequence of quantum mechanics operating without artificial constraints. We experience time as a river that flows in only one direction, from past to future, never backward, and this fundamental asymmetry shapes every aspect of our existence and perception of reality. When we observe a cup of coffee cooling on a table, we see it gradually lose heat until it reaches room temperature, and we intuitively understand that this process cannot reverse itself spontaneously, that the coffee will never spontaneously heat up again while the room grows colder, and this directional quality of time, which physicists call the arrow of time, seems to embed itself into the very fabric of how we understand causality and consequence. Yet here emerges a profound puzzle that has troubled physicists and philosophers for more than a century. The fundamental laws of physics, from Newton's equations to Einstein's relativity and even quantum mechanics, are remarkably time-symmetric, meaning that if we were to reverse the direction of time in our mathematical equations, they would still produce valid descriptions of how the universe behaves, suggesting that at the deepest level, nature itself should have no preference for past over future. The resolution appears to lie in entropy and the second law of thermodynamics, which states that disorder in an isolated system tends to increase over time, and this statistical tendency toward chaos provides the universe with a genuine directional arrow, because while individual particles follow time-symmetric laws, the probability that billions upon billions of particles will spontaneously organize toward greater order while disorder decreases is so astronomically minuscule that it effectively never occurs. Consider the possibility that time, as we experience it, is not a fundamental feature of the universe, but rather an emergent phenomenon that arises from deeper, more basic physical structures. In this view, time does not exist at the bedrock level of reality. Instead, it crystallizes into being through the complex interactions of quantum entanglement, entropy, and information processing at scales we have yet to fully understand. At the quantum level, the equations governing particle behavior contain no inherent arrow of time, no preferred direction that distinguishes past from future, yet our macroscopic experience insists that time flows decisively in one direction only. This paradox suggests that temporality might be something that bubbles up from quantum complexity rather than something woven into the fabric of existence from the start. The physicist Carlo Rovelli and others working in quantum gravity have proposed that time emerges when quantum systems become sufficiently complex and entangled, creating the appearance of causality and sequence through the lens of thermodynamic processes and information flow. What we call the present moment, the sensation that now is special and distinct from past and future, may itself be an artifact of how our brains process information and construct narratives about reality rather than a property of the cosmos itself. We have become so accustomed to experiencing time as a river flowing from birth toward death, from yesterday into tomorrow, that we rarely question whether this chronological structure reflects something objectively real or merely represents a useful cognitive framework that evolution has equipped us to construct. The mind creates temporal coherence from quantum events that, in their purest form, contain no temporal coherence at all, organizing them into stories with beginnings, middles, and endings that feel inevitable and absolute, even though they might represent nothing more than one particular way of packaging information about reality, one interpretation among countless others that the universe does not inherently favor or require. In the first fraction of a second after the Big Bang, the universe underwent an exponential expansion so violent and so rapid that it defies conventional understanding, a phenomenon we call cosmic inflation, where space itself stretched and expanded at speeds far exceeding the speed of light, growing from subatomic dimensions to galactic scales in what physicists measure in mere slivers of time. This theory emerged in the early 1980s when cosmologist Alan Guth recognized that the standard Big Bang model contained troubling inconsistencies, particularly the horizon problem, which asked why distant regions of the universe that could never have communicated with each other nonetheless possessed nearly identical temperatures and physical properties, a puzzle that seemed unsolvable until Guth proposed that if space had once expanded exponentially fast, it could have carried vastly different regions into causal contact before inflation separated them again. The mechanism behind cosmic inflation operates through what physicists call the inflaton field, a hypothetical quantum field permeating all of space whose energy density creates a state of negative pressure, causing space to accelerate outward in a self-amplifying feedback loop where the expansion generates more space, which contains more inflaton field energy, which drives further expansion, a process that continues until the field decays and releases its energy as heat and particles. Seeding the initial conditions for the Big Bang nucleosynthesis, we observe. What if reality itself is not what we perceive it to be, but rather an intricate computational construct designed and operated by an advanced civilization existing at a higher level of reality? The simulation hypothesis posits that the universe we inhabit, complete with all its physical laws, fundamental particles, and conscious observers, might be nothing more than an elaborate digital simulation created by beings whose technological capabilities far exceed our current understanding. This theory emerges from a logical chain of reasoning. If humanity continues advancing technologically at an exponential rate, then eventually our descendants or some post-human civilization will possess the computational power necessary to create fully immersive simulations indistinguishable from base reality, populated with conscious artificial beings. If such simulated universes can be created, and if many of them could exist simultaneously, then statistically speaking, we are far more likely to be living inside one of these countless simulations than in the original base reality, simply due to the sheer numerical probability involved. The psychological mechanism driving this theory's persistence lies in humanity's ancient tendency to question the nature of existence itself, reimagined through a modern technological lens. We have always wondered whether we are real or dreaming, whether we are puppets of divine creation, whether we are trapped in Plato's cave observing shadows on a wall rather than reality itself. The simulation hypothesis merely updates these timeless philosophical questions with contemporary vocabulary drawn from computer science, artificial intelligence, and quantum mechanics. What makes this hypothesis particularly compelling despite its unfalsifiability is that it leverages real scientific observations about the mathematical nature of physics, the digital properties of quantum mechanics at the smallest scales, and the apparent fine-tuning of universal constants that seem precisely calibrated for complexity to emerge. Imagine that every black hole in our universe contains within it an entirely separate universe, complete with its own stars, galaxies, planets, and perhaps even conscious observers looking up at their own night skies in wonder. This hypothesis, explored seriously by physicists including Lee Smolin and others working in quantum gravity research, suggests that black holes are not merely destructive cosmic vacuums, but rather portals to entire pocket universes born from the collapse of massive stars. According to this theory, when matter falls past the event horizon and enters the black hole, it does not simply vanish into oblivion, but instead continues into a new spacetime structure, where the singularity becomes the Big Bang of an infant universe. The mechanism behind this concept rests on a fundamental reinterpretation of what happens at the quantum level during gravitational collapse, where the classical prediction of infinite density gives way to something far more exotic, a transition between separate dimensional spaces. Furthermore, this theory suggests a kind of cosmic reproduction where universes spawn new universes through black holes, creating an infinite tree of existence where our own universe might be the interior of some enormous black hole within a parent universe. The appeal of this hypothesis lies partly in how elegantly it addresses several paradoxes in modern physics, including the information loss problem that has plagued black hole thermodynamics for decades. Yet despite its mathematical intrigue and the serious consideration it receives in academic circles, we continue to inhabit a reality where we cannot directly observe these alleged inner universes, cannot test their properties, and cannot verify whether conscious beings might exist within them observing phenomena we consider fundamental. Imagine a pathway through spacetime so intricately folded that it loops back upon itself, allowing a traveler to arrive at a destination before they ever departed, creating a closed loop in causality where effect precedes cause and the future influences the past in ways that defy our ordinary understanding of temporal progression. This is the concept of a closed timelike curve, a theoretical solution permitted by Einstein's equations of general relativity that describes a trajectory through the fabric of spacetime itself that is self-intersecting in time. Within the mathematical framework of general relativity, which has been validated by countless observations from the orbit of Mercury to the detection of gravitational waves, closed timelike curves emerge not as mathematical errors or artifacts, but as legitimate geometric possibilities, suggesting that the universe might permit such causal paradoxes under certain extreme conditions involving rotating black holes, traversable wormholes, or exotic matter configurations. The mechanism underlying this possibility is profoundly counterintuitive. The equations do not forbid it. They merely describe the geometry of a universe where time is not an absolute universal constant flowing uniformly in one direction, but rather a flexible dimension intimately woven with space, bending and curving in response to mass and energy, just as space itself does. Yet despite these sound mathematical foundations, closed timelike curves remain purely theoretical and have never been observed, and physicists continue to grapple with the logical consequences. If such curves could exist, they would permit time travel and grandfather paradoxes where one could theoretically prevent one's own existence, violations of causality that seem to contradict the fundamental order of reality itself. Imagine a time traveler who journeys backward through the corridors of history with a singular, dark purpose, confronting their own grandfather before that ancestor ever met their grandmother, and in a moment of calculated determination, preventing that fateful meeting or eliminating the grandfather entirely, which would mean the time traveler's parent would never be born, which would mean the time traveler themselves would never exist, and yet here they stand in the past, very much alive and present, having just committed the act that should have erased them from reality itself. This is the grandfather paradox, perhaps the most famous and most troubling logical contradiction that emerges whenever we seriously consider the possibility of backward time travel, and it has haunted physicists, philosophers, and science fiction writers for over a century. The paradox reveals a fundamental incompatibility between the freedom we assume we possess in our actions and the fixed nature of history as we observe it, because if you could travel to the past and change events, then history would no longer be fixed. Yet we know history is fixed because it has already happened, and we are here to observe its results. The paradox persists in our collective imagination, despite the fact that it reveals something genuinely troubling about the nature of causality and determinism, because the very concept of time travel captures our deepest hopes and fears about our own agency and the mutability of the world around us. We continue to explore this paradox in literature and thought experiments because it forces us to confront uncomfortable truths about whether the past is truly immutable, whether the future is predetermined, and whether free will can coexist with a universe governed by the laws of physics, making it less a practical problem and more a window into the fundamental structure of reality itself. In the year 2021, physicists achieved something that seemed to violate the most fundamental law of physics, discovering structures called time crystals that break temporal symmetry in ways that should be theoretically impossible. A time crystal is a quantum system that repeats in time just as an ordinary crystal repeats in space, maintaining a periodic structure across temporal dimensions without requiring any external energy input to sustain its pattern. Researchers at Google and other institutions created these exotic states of matter by manipulating quantum systems with precisely calibrated laser pulses, observing that the system would spontaneously return to its initial state at regular intervals, creating a temporal pattern that cycles endlessly without degradation or energy decay. This phenomenon directly challenges the second law of thermodynamics, which dictates that isolated systems must always move toward greater disorder and entropy, suggesting that time crystals represent a new category of matter that exists in eternal motion while remaining in perfect equilibrium. The mechanism behind this apparent contradiction relies on a subtle distinction between symmetry breaking in space and symmetry breaking in time itself, where the system's repetitive nature emerges not from external driving forces but from the intrinsic quantum properties of the atoms involved, creating what physicists call discrete time translation symmetry breaking. What makes time crystals particularly mind-bending is that they appear to achieve perpetual motion without violating any known laws, because the pattern of repetition itself becomes the fundamental state of the system, and no energy is actually being extracted from the motion, only the temporal structure is being maintained. If black holes represent regions of spacetime where gravity has become so intense that nothing, not even light, can escape their crushing pull, then white holes exist as their theoretical inverse, hypothetical cosmic phenomena from which matter and energy could only emerge, never to be drawn inward, functioning as one-way exits from the universe rather than one-way entrances. White holes exist purely as mathematical solutions to Einstein's field equations of general relativity, appearing symmetrically alongside black hole solutions. Yet unlike black holes, they have never been observed, detected, or confirmed to exist anywhere in the cosmos despite decades of astronomical observation and sophisticated instrumentation. The concept emerges from the realization that the equations of general relativity are time-reversible, meaning that if you reverse the direction of time in the equations describing a black hole, you mathematically obtain a white hole, leading physicists to ask whether these time-reversed objects might possess physical reality in our universe. Some theoretical physicists have speculated that white holes could explain certain astrophysical phenomena such as gamma-ray bursts or the violent jets of energy ejected from active galactic nuclei, though evidence for this remains purely conjectural and no mainstream consensus supports these interpretations. The psychological appeal of white holes lies partly in our desire for symmetry and balance in nature, the notion that if inescapable black holes exist, then perhaps outward-flowing white holes must also exist somewhere, restoring a sense of cosmic equilibrium and complementarity that feels philosophically satisfying even if empirically unsupported. Imagine standing before a vast cosmic canvas where everything you perceive, every star, every galaxy, every quantum particle that comprises your own body, exists as nothing more than a projection cast from information encoded on a distant boundary, much like a three-dimensional movie playing out from a two-dimensional screen that lies infinitely far away at the edge of space itself. This is the essence of the holographic principle, a theoretical framework suggesting that all the information contained within a volume of space can be completely described by information residing on its outer surface, a mathematical boundary as thin as a whisper, yet somehow containing the entirety of what we experience as reality. The principle emerged from studies of black holes by physicist Juan Maldacena in the late 1990s, who discovered a profound mathematical relationship between gravitational theories in higher dimensional spaces and quantum field theories existing in lower dimensional spaces, suggesting that our three-dimensional universe might be fundamentally holographic in nature, a projection rather than something genuinely three-dimensional in its deepest essence. What makes this theory so conceptually striking is how it inverts our intuitive understanding of dimensionality and information. We naturally assume that a three-dimensional space contains more information than its two-dimensional boundary, yet the mathematics of quantum gravity and thermodynamics suggest the opposite is true, that a universe's boundary contains precisely as much information as everything within it, no more and no less. This principle persists in modern theoretical physics not because we have direct observational evidence, but because it solves profound inconsistencies between general relativity and quantum mechanics, because it elegantly explains black hole entropy, and because the mathematics works with such stunning precision that physicists across institutions continue developing and refining holographic models. Consider that time itself might not be a fundamental feature of the universe, but rather an emergetic property that arises directly from the arrow of entropy, that inexorable tendency for disorder to increase in all isolated systems. In this framework, the past is defined not by temporal distance, but by states of lower entropy, while the future unfolds toward states of ever-increasing disorder and randomness. The reason we experience time as directional, moving relentlessly from order to chaos, from memory to uncertainty, is because entropy provides the only genuine arrow that points in one direction through the cosmos. When you observe a cup of coffee cooling on a table, you are witnessing entropy in action, and that process itself defines what we mean by the forward passage of time. The universe began at the moment of lowest possible entropy, the Big Bang, a state of perfect order and compression, and has been moving toward maximum entropy ever since, and this journey is what we call time itself. The human experience of memory functions only because our brains store information as increasingly disordered states, and we can only remember the past because entropy has made it fixed and unchangeable, while the future remains open precisely because it has not yet reached its final state of maximum disorder. Without entropy, there would be no distinction between past and future, no arrow pointing in a particular direction, no sense of causation or consequence, and therefore no time as we understand it. This theory suggests that conscious beings like ourselves only perceive time because we are embedded within systems that are constrained by entropy, that we experience the flow of moments because we ourselves are subject to the same irreversible processes that govern all matter and energy. The psychological mechanism that locks us into temporal experience is therefore not some mysterious feature of consciousness or dimension of space, but simply our intimate participation in the thermodynamic reality of the universe, our inescapable involvement in the transformation of order into chaos. Imagine standing at the edge of a map where the continents suddenly end and the parchment simply stops, leaving you wondering what lies beyond that final border. And this fundamental human anxiety about boundaries and endings is precisely what theoretical physicists James Hartle and Stephen Hawking sought to address when they proposed their no-boundary proposal in the 1980s, a mathematical framework suggesting that the universe has no beginning and no end in the traditional sense. Much like the surface of a sphere which is finite yet has no edge or boundary where it terminates. The proposal emerges from the marriage of quantum mechanics and general relativity, two frameworks that have historically resisted unification, and it works by reimagining time itself as a spatial dimension that curves back on itself in quantum gravity, suggesting that at the moment of the Big Bang, time does not extend backward infinitely, but rather loops around, making the question of what came before the Big Bang fundamentally meaningless because there is no before. Only the curvature of spacetime itself folding back on what we perceive as the origin of all things. This conception eliminates the logical problem that has plagued cosmologists for centuries, the uncomfortable necessity of requiring an external cause for the universe itself. Since a universe with no boundary requires no creator and no external impetus to spring into being, as it simply exists as a self-contained mathematical entity where past and future merge seamlessly in the geometry of spacetime. What persists despite the counterintuitive nature of this model is our deep psychological need to understand time as having a clear direction, a definite start and a predicted finish. Yet the no-boundary proposal asks us to abandon these comforting notions and accept that the universe may operate according to principles utterly foreign to our intuitive experience, where cause and effect blur, where time becomes just another dimension of space, and where the very concept of a beginning loses all meaning in the quantum foam from which reality emerges. When physicist Stephen Hawking introduced the concept of imaginary time in the context of quantum cosmology, he was proposing something that fundamentally challenges our intuitive understanding of how the universe works, suggesting that at the moment of the Big Bang, time itself may not have existed in the conventional sense we experience it, but rather as a mathematical construct perpendicular to real time, existing in what physicists call the imaginary plane. In this framework, time is treated as an imaginary number, a mathematical entity that exists only in equations and theoretical spaces, not as the forward-moving arrow we perceive in our daily lives where moments flow inexorably from past through present into future. The mechanism behind this concept rests upon quantum mechanics and general relativity, two pillars of modern physics that describe reality at scales from the subatomic to the cosmic, yet which produce contradictory results when applied simultaneously to the universe's earliest moments, creating what physicists call a singularity where conventional mathematics breaks down entirely. By replacing time with an imaginary temporal dimension near the Big Bang, Hawking and others discovered that the mathematical contradictions vanish. The universe becomes describable as a finite, boundless four-dimensional sphere that requires no external cause or boundary condition, fundamentally eliminating the logical problem of what came before time itself began. This theoretical move is profoundly abstract and counterintuitive because it suggests that the concept of causality, of one moment causing the next, may be an emergent property that only becomes real as the universe cools and expands away from its initial quantum state, while at the absolute beginning, cause and effect themselves are merely features of how our minds organize reality rather than fundamental properties of existence. In the vast landscape of cosmological theories, eternal inflation presents a mind-bending perspective on the nature of our universe's origins and its ultimate fate, suggesting that the Big Bang was not a singular, isolated event, but rather one bubble among countless others in an endless cosmic foam. Proposed most rigorously by physicist Andre Linde in the 1980s, eternal inflation describes a universe where inflation, the exponential expansion that occurred in the first fractions of a second after the Big Bang, never truly stops across all regions of space simultaneously, instead continuously generating new bubble universes in different regions of an ever-expanding cosmic landscape. The mechanism behind this theory rests on quantum mechanics applied to the inflationary field itself, which behaves like a landscape with valleys and peaks, and while most of the field settles into a lower energy state and inflation ceases in that region, quantum fluctuations in other regions keep pushing the field back up the slope, causing those areas to continue inflating and spawning new universes with potentially different physical laws and constants. What makes eternal inflation so conceptually unsettling is that it transforms our universe from a unique creation event into something far more ordinary and cyclical, suggesting that somewhere in this infinite cosmic structure, new Big Bangs are perpetually igniting, each giving birth to a separate universe with its own chemistry, physics, and perhaps even its own conscious observers pondering their origins. The theory has persisted in mainstream cosmology despite producing inherent philosophical challenges, including the measure problem, which makes calculating probabilities in an infinite multiverse deeply problematic, and the unfalsifiability issue that makes it extraordinarily difficult to test empirically, since we cannot observe these other universes beyond our cosmic horizon. Imagine the cosmos not as a single, unified reality, but as an infinite foam of disconnected universes, each one a distinct bubble floating in an endless void, each with its own physical laws and constants that emerged from the quantum vacuum in moments of cosmic inflation. This is the essence of the bubble universe theory, also known as eternal inflation, which suggests that the Big Bang was not a singular event that created everything, but rather one bubble among countless others, born from an eternally inflating quantum field where new universes continuously nucleate into existence like bubbles rising through champagne. The psychological appeal of this theory lies in its radical reframing of what existence means, transforming our universe from the sole reality into one neighborhood among infinite neighborhoods, each potentially harboring different versions of physics, chemistry, and the possibility of life itself. The mechanism behind this concept emerges from the mathematics of inflationary cosmology, particularly the work of physicists like Andre Linde, who demonstrated that once inflation begins, it never truly stops everywhere simultaneously, but rather continues eternally in some regions while ending in others, creating what physicists call eternal inflation. What persists in our fascination with bubble universes despite its untestable nature is the way it resolves certain cosmological puzzles and extends the principle of mediocrity even further than we initially dared, suggesting that our universe's particular set of constants and conditions might simply reflect the vast statistical probability of existence itself across infinite domains. We have normalized this concept by incorporating it into serious theoretical physics discussions and treating it as a logical extrapolation of well-established inflationary mathematics, even as it takes us into territories where empirical verification becomes fundamentally impossible, where we must rely entirely on the elegance and internal consistency of the mathematics rather than observational evidence. Imagine a cosmos that does not begin with a singular explosive moment, but rather emerges from the collision of two vast, multidimensional membranes floating through higher dimensional space, and you have encountered the Ekpyrotic Universe theory, a fascinating alternative to the Big Bang that reimagines the very foundation of existence itself. The word ekpyrotic derives from an ancient Greek philosophical concept meaning conflagration or burning, referring to the cyclical destruction and recreation of the universe. And this modern theoretical framework suggests that what we perceive as the beginning of time might actually represent the violent meeting of two parallel sheets of spacetime existing in dimensions beyond our direct perception. According to this model, developed primarily by physicists including Justin Cowery and Paul Steinhardt, our three-dimensional universe occupies a brane, or membrane, while another identical brane exists nearby in an extra dimension. And periodically these cosmic structures collide with such tremendous force that the energy release triggers what we observe as the Big Bang and the subsequent expansion we call cosmic inflation. The psychological appeal of this theory rests partly on its resolution of certain puzzles that plague standard Big Bang cosmology, particularly questions about why the universe appears so extraordinarily uniform and flat, and why it contains the precise amount of matter and energy necessary for stars, galaxies, and ultimately conscious life to emerge, problems that inflation theory attempts to solve, but which the ekpyrotic model addresses through an entirely different mechanism. Rather than invoking a rapid exponential expansion of space itself, the ekpyrotic universe relies on the elegant geometry of higher dimensions and the inevitable physics of colliding membranes to explain these observations, suggesting that what inflation accomplishes through brute force expansion might instead result from the geometric properties of our universe as a brane moving through higher dimensional space. In the landscape of modern theoretical physics, brane collision cosmology presents a radical reimagining of how our universe began, drawing from the mathematical frameworks of string theory and higher dimensional geometry to suggest that the Big Bang itself may have been the catastrophic collision of multidimensional membranes floating through a higher dimensional space. According to this theory, our three-dimensional universe is not the fundamental reality, but rather a three-dimensional brane or membrane existing within a larger 10 or 11-dimensional space called the bulk. And what we perceive as the beginning of time was actually the moment when our brane violently collided with another brane moving through this higher dimensional void, releasing unimaginable amounts of energy that manifested as the explosive expansion we call the Big Bang. The psychological appeal of this theory lies in its ability to solve several perplexing cosmological problems simultaneously. It explains why the universe exploded into existence without requiring a miraculous singularity of infinite density. It provides a natural mechanism for inflation through the collision itself. And it elegantly sidesteps the question of what came before time by suggesting that before our brane collision, different physical laws and perhaps different arrows of time governed other branes in the bulk. What makes brane collision cosmology particularly compelling to theoretical physicists is how it extends beyond mere speculation about the past to make predictions about the future, suggesting that our universe might eventually collide with another brane, creating a cyclic universe that endlessly repeats through successive collisions and expansions, a concept known as the Ekpyrotic Universe. At the smallest scales of reality, beneath electrons and quarks and the fundamental particles we believe constitute matter itself, physicists have proposed the existence of something far stranger than anything we can directly observe: quantum foam, a seething, turbulent sea of virtual particles constantly erupting into existence and vanishing in the blink of an eye. This concept emerges from the marriage of quantum mechanics and general relativity, two frameworks that describe the universe at scales so disparate that they have historically refused to work together. Yet when we push our mathematical models to the absolute limits of smallness, to distances near the Planck length, approximately 1/10 billionth of a trillionth of an inch, spacetime itself seems to lose its smooth, continuous character, and instead becomes fractured, foaming, and wildly uncertain. In this quantum foam, the very fabric of existence vibrates with uncertainty, with particles and antiparticles spontaneously manifesting and annihilating in intervals so brief that no observer could ever directly confirm their presence. Yet their effects might still ripple outward to influence larger scales through a cascade of quantum effects that accumulate into measurable consequences in our macroscopic world. The mechanism that permits this mind-bending vision rests upon the uncertainty principle, which mandates that energy and time are inversely related. The shorter the time span we consider, the greater the energy fluctuations permitted by the laws of physics, meaning that in the infinitesimal fractions of time that define the quantum foam's existence, arbitrarily large amounts of energy can briefly exist as borrowed debt from the vacuum itself. Imagine a ball resting in a shallow valley on a hillside, seemingly stable and secure in its current position, yet unaware that just beyond the rim of that valley lies a far deeper canyon where it could roll and settle at a much lower energy state. This is the essence of the false vacuum theory, a concept from quantum field theory that suggests our universe might not exist in its lowest possible energy state, but rather in a metastable state, a temporary resting place suspended above a true ground level of stability. According to this theory, the quantum fields that permeate all of space, the very fabric underlying particles and forces, are not necessarily at their minimum energy configuration. Instead, they may be trapped in what physicists call a false vacuum, a local minimum where they appear stable, but where an even lower energy state exists elsewhere in the dimensional landscape. The mechanism that maintains this precarious situation involves quantum tunneling and energy barriers, invisible walls in the quantum realm that keep our universe locked in its current configuration. Under normal circumstances, the energy required to escape this false vacuum state is so extraordinarily high that it seems impossible for such a transition to occur naturally. Yet quantum mechanics permits tunneling events where particles and fields can spontaneously pass through barriers that should be impenetrable according to classical physics. If the false vacuum were ever to decay, even through the infinitesimal probability of quantum tunneling, the consequences would be apocalyptic beyond human comprehension, as the fields would collapse into their true ground state in a catastrophic phase transition, releasing unimaginable energy and fundamentally altering the laws of physics across the entire observable universe. Imagine a system so perfectly isolated that it exists in complete equilibrium with itself, sealed away from all external interference, and then consider what Henri Poincaré proved mathematically in the late 1800s. That given enough time, this closed system must eventually return to a state arbitrarily close to its initial condition, cycling through its past configurations again and again in an eternal recurrence that seems to defy the forward march of entropy and the arrow of time itself. In a finite universe with finite energy and finite possible states, the mathematical logic becomes inescapable. If a system has only a limited number of configurations it can occupy, and if those configurations must be explored randomly or cyclically, then sooner or later the system will pass through the same arrangement of particles and forces that existed at some earlier moment, creating a kind of cosmic return that makes the distant past inevitably our distant future. This theorem operates through a purely combinatorial mechanism, where the universe, treated as a closed thermodynamic system with finite degrees of freedom, must exhaust its possibilities and begin repeating itself. Much like shuffling a finite deck of cards will eventually produce the exact same arrangement you began with if you shuffle long enough, though the timescale involved may vastly exceed the current age of the universe by factors so enormous they become almost meaningless to human comprehension. Yet despite the rigorous mathematics supporting this idea, we have normalized a fundamentally different understanding of reality, one where time flows irreversibly forward, where the past grows ever more distant and unrepeatable, where entropy always increases and disorder spreads without bound, building entire frameworks of physics and philosophy around a directional arrow of time that Poincaré Recurrence seems to undermine, suggesting instead that all things must eventually return. That nothing is truly lost, but only temporarily hidden in the vast configuration space of possibility, waiting through eons to emerge once more from the cosmic shuffle. Quantum immortality is a thought experiment that emerges from the many worlds interpretation of quantum mechanics, suggesting that, from a subjective perspective, consciousness may never experience its own death because it always finds itself in branches of reality where survival occurred. Imagine a scenario where a quantum event with a 50-50 probability of two outcomes determines whether you live or die in any given moment. And according to many worlds theory, both outcomes actually occur across different branches of the universe, creating two separate realities where both the living and dead version of you exists simultaneously. The disturbing implication is that while other people will observe your death across most branches of reality, your own consciousness, by the mathematical nature of quantum branching, will persist in ever-narrowing pathways where improbable survival events keep occurring, meaning you would subjectively experience an increasingly bizarre and unlikely sequence of near-death escapes, miraculous survivals against astronomical odds. And perhaps eventually find yourself as the sole conscious observer in an increasingly degraded or strange universe, where the laws of probability have twisted to accommodate your continued existence. This concept troubles physicists and philosophers alike because it suggests that while the external world evolves normally, any individual consciousness trapped in this framework would experience something akin to immortality, not through any supernatural means, but through the relentless mathematics of quantum mechanics and branching timelines. The mechanism hinges on the distinction between the objective probability of your death across all branches, which approaches certainty, and the subjective probability from your own first-person perspective, which your consciousness theoretically never experiences directly because you cannot experience branches where you are dead. In 1949, the mathematician Kurt Gödel, already famous for his incompleteness theorems that shook the foundations of logic itself, turned his attention to Einstein's field equations of general relativity and discovered something that should have been impossible. Within the mathematical framework that describes how space and time curve around matter and energy, Gödel found an exact solution describing a universe that rotates as a whole, spinning like a cosmic top through the void of spacetime itself. This universe possessed a peculiar and deeply troubling property that Gödel realized with both precision and philosophical dread. Within such a rotating cosmos, closed time-like curves could exist, meaning that the geometry of spacetime would permit an observer to travel backward through time and arrive at their own past, creating paradoxes and violating the very notion of causality that we assume governs reality. The mechanism behind this strange prediction emerges from the marriage of rotation and gravitation in ways our intuition finds almost impossible to accept. As spacetime curves and twists around a rotating mass distribution, the very fabric of temporal ordering becomes sufficiently warped that future and past cease to be universal concepts, instead becoming directional matters dependent on one's path through the cosmos. What makes Gödel's solution particularly unsettling is not merely its mathematical validity, which Einstein himself verified, but rather that we have never observed such a universe. Yet we cannot prove it is impossible, and so we continue living with the uncertainty that our cosmos might be rotating, might possess closed time-like curves, might permit paradoxes that our minds refuse to genuinely contemplate. Imagine a tunnel through spacetime itself, a bridge that connects two distant points in the universe, or perhaps two different moments in time, allowing a traveler to slip through the fabric of reality and emerge not just in a different location, but in a different era altogether. This is the concept of wormhole time travel, a theoretical possibility that emerges directly from Einstein's general relativity, which describes gravity not as a force pulling objects downward, but as a curvature of spacetime itself created by the presence of matter and energy. When physicists began exploring the mathematical solutions to Einstein's field equations, they discovered something remarkable. The equations allow for the existence of traversable wormholes, also called Einstein-Rosen bridges, which could theoretically function as shortcuts through space and potentially through time. To achieve this, one would need exotic matter with negative energy density, something that might exist in the form of dark energy or could potentially be created through advanced technology far beyond our current capabilities. The mechanism relies on the idea that if you could create a rotating or charged wormhole and manipulate its properties with precisely calibrated exotic matter, you might be able to establish a closed time-like curve, a path through spacetime that loops back on itself, allowing causality itself to bend. What makes this concept persist in serious scientific discourse, despite the enormous practical and theoretical obstacles, is that it does not explicitly violate the known laws of physics as we understand them, unlike faster-than-light travel, which would contradict special relativity. The equations work on paper, the mathematics holds together, and the solutions exist within the framework that has proven remarkably accurate in describing everything from planetary orbits to black holes to gravitational waves. Imagine standing at a crossroads in time itself, where the very fabric of causality seems to bend under the weight of impossible scenarios, and yet somehow, everything that happens was always meant to happen in exactly that way. Novikov Self-Consistency, named after physicist Igor Novikov, presents one of the most elegant solutions to the paradoxes that plague time travel theory, particularly the grandfather paradox that has haunted physics and philosophy for generations. The theory proposes that if a time traveler were to journey backward through the corridors of history with the explicit intention of preventing their own birth or altering a crucial historical event, the universe itself would conspire against them through an invisible web of probabilities and circumstances, ensuring that their actions ultimately fail to create any contradiction whatsoever. This is not some external force physically preventing them from pulling the trigger or speaking the fatal words, but rather a profound principle of consistency woven into the very nature of spacetime itself, where events arrange themselves in such a manner that whatever happens has always happened and must happen, creating a closed causal loop that permits time travel without paradox. The mechanism underlying this theory rests upon the notion that the universe is fundamentally self-correcting, that probability itself aligns against any action that would generate logical contradiction, subtly redirecting circumstances, influencing chance encounters, or placing obstacles in the path of the time traveler until their intentions are thwarted in ways that seem entirely natural and inevitable. What makes Novikov's self-consistency so philosophically profound is that it suggests we inhabit a deterministic universe where free will becomes illusory only at the boundaries of causality, where history is not merely a record of what happened but a locked structure that cannot be broken. Yet the time traveler themselves remains convinced throughout that they possess genuine choices and agency in their actions. In the theoretical landscape of general relativity and quantum mechanics, physicist Stephen Hawking proposed in 1992 what became known as the chronology protection conjecture, a hypothesis suggesting that the laws of physics actively prevent the occurrence of closed time-like curves, or in simpler terms, they prevent time travel to the past and the resulting paradoxes that would inevitably emerge from such journeys. The conjecture arose not from observational evidence but from a deep logical concern. If time travel backward were physically possible, then causality itself would collapse, allowing effects to precede causes and enabling grandfather paradoxes where a traveler could theoretically eliminate their own birth, creating logical impossibilities that seem to violate the fundamental structure of reality itself. Hawking's proposal suggests that rather than being merely improbable or unlikely, closed time-like curves would be actively forbidden by some yet undiscovered principle or mechanism in physics, much like how entropy prevents perpetual motion machines, or how the uncertainty principle prevents simultaneous knowledge of both position and momentum. The elegance of this conjecture lies in its assertion that nature itself has built-in protections against logical contradictions, that the universe, through its deepest physical laws, maintains an internal consistency by rendering certain seemingly theoretically possible scenarios actually impossible in practice. What makes this conjecture particularly intriguing is that despite decades of theoretical physics research, no definitive mechanism preventing time travel has been empirically identified or mathematically proven absolutely. Yet time travel to the past has never been observed, suggesting either that Hawking's intuition captures something true about reality's structure, or that the universe simply operates under constraints we have not yet mathematically formalized. Imagine universes not as isolated islands of reality, but as offspring in an endless cosmic family tree, each one birthed from the quantum collapse of black holes within its parent universe. This is the essence of cosmological natural selection, a theory proposed by physicist Lee Smolin in the 1990s, which suggests that universes reproduce through black hole formation, and that the laws of physics themselves are subject to evolutionary pressure across multiple universes. According to this framework, when a black hole forms and collapses into a singularity, it does not simply disappear, but rather spawns a new universe with slightly altered physical constants and laws, much like genetic mutations in biological organisms. The mechanism behind this theory rests on a profound logical inversion. Rather than asking why our universe seems so finely tuned for life, we might instead ask whether universes that produce many black holes, and therefore create many offspring universes, would naturally become more common in the multiverse over cosmic time. The universes that generate the most black holes would have the greatest reproductive success, leading to a natural selection process operating at the grandest scales imaginable. This creates a strange feedback loop, where physical constants that favor black hole production would proliferate throughout the multiverse. And since the conditions necessary for black holes often overlap with conditions favorable for stellar formation and ultimately biological life, our universe's apparent fine-tuning could be explained not through miraculous coincidence or divine design, but through cosmic heredity. What makes this theory particularly compelling is how it transforms the bewildering improbability of our existence into something resembling a natural process. Yet it remains deeply contentious, because it seems to suggest an infinite regress of universes, each spawning from another, with no clear beginning or ultimate explanation for where the first universe came from, or why the rules of black hole reproduction should hold across all universes eternally. Imagine that within the quantum foam at the smallest scales of reality, new universes are constantly being born, sprouting from the fabric of spacetime like branches from an infinite tree, each one with its own set of physical laws, constants, and possibilities that may differ radically from our own. This is the concept of baby universes, a theoretical framework that emerged from the work of physicists like Lee Smolin and has roots in earlier speculations about quantum mechanics and the nature of black holes. According to this idea, when a black hole forms and eventually evaporates through Hawking radiation, it might not disappear completely into nothingness, but rather pinch off from our universe to create a new, separate pocket of spacetime where entirely different realities unfold according to entirely different rules. The mechanism underlying this theory rests on the mathematics of general relativity and quantum field theory, which permit solutions where wormholes or Einstein-Rosen bridges could connect universes, or where quantum tunneling events at the Planck scale could spawn new cosmic domains. Some physicists have proposed that our own universe might have been born in such a manner, budding from a parent universe through a process so ancient that all evidence of the connection has long since disappeared beyond any possible observation. What renders baby universes so intellectually compelling despite their complete lack of empirical confirmation is how they address the profound question of why our universe exists at all, and why it possesses the particular characteristics it does. The theory suggests that universes might reproduce, evolve, and compete in a kind of cosmic Darwinian process, where universes capable of producing black holes create more offspring universes, leading to a fractal-like multiverse that favors the creation of universes similar to our own. Yet the notion persists in serious physics literature precisely because it attempts to weave together quantum mechanics, general relativity, and cosmology into a coherent narrative, even as it remains forever beyond the reach of any possible experimental verification. Black hole cosmology presents a radical proposition, that our universe itself might be contained within a black hole, and that black holes might themselves contain universes. This theory emerges from the observation that the mathematical properties describing black hole interiors bear striking resemblance to the mathematical properties describing our expanding universe, particularly in how both exhibit event horizons beyond which information and causality appear fundamentally altered. When physicists began examining the equations governing black hole thermodynamics and comparing them to cosmological models of universal expansion, they noticed an uncanny parallel, suggesting that what we perceive as the beginning of our universe in the Big Bang might actually represent the perspective of matter falling through an event horizon, where time and space exchange their fundamental roles. The mechanism underlying this theory rests on the principle that the distinction between inside a black hole and outside the universe may be purely perspectival rather than ontologically distinct, and that recursive levels of cosmic organization might exist indefinitely, with each universe spawning black holes that birth new universes within them. This creates a kind of infinite hierarchical nesting, where our universe, our solar system, and even our planet could simultaneously be both a contained system and a container for other systems. Despite the lack of empirical verification and the profound conceptual difficulties in testing such a hypothesis, this framework persists in theoretical physics because it offers an elegant mathematical consistency and resolves certain paradoxes in quantum gravity and cosmological singularities. For much of the 20th century, astronomers and cosmologists found themselves locked in a profound debate about the very nature of the universe itself. And one of the most compelling alternatives to the Big Bang theory emerged in the form of the steady-state theory, a model that proposed the universe had no beginning and would have no end, existing in a perpetual state of dynamic equilibrium across all of time. This theory suggested that while the universe was indeed expanding, it maintained a constant average density by the continuous creation of new matter throughout space, a process so infinitesimally slow that it would never be observable at human scales, yet sufficient to replace the matter being drawn apart by cosmic expansion. The psychological appeal of this theory lay in its elegant simplicity and its profound philosophical comfort, for it eliminated the need for a creation event, sidestepped troubling questions about what came before the universe began, and offered a cosmos that required no transcendent cause beyond itself. The theory's proponents, including Fred Hoyle, Hermann Bondi, and Thomas Gold, found that this framework resonated deeply with their intuitions about causality and infinity, suggesting that a truly eternal universe might operate under principles of perfect uniformity across all times and places. What made the steady-state theory particularly compelling was how it provided a rational-sounding alternative to what many scientists initially viewed as the almost religious implications of the Big Bang model. Yet the theory persisted in academic circles and undergraduate textbooks long after observational evidence, particularly the discovery of the cosmic microwave background radiation in 1965, had fundamentally undermined its core predictions. Even as telescopic observations revealed that the universe looked dramatically different in the distant past than it does today, contradicting the fundamental assumption of uniform appearance across time, the theory maintained surprising cultural resilience, becoming embedded in popular imagination as a legitimate scientific possibility. Imagine a universe that does not exist all at once, stretching backward and forward through time as a complete and finished tapestry, but rather one that is constantly being created, moment by moment, in an endless present that perpetually generates reality fresh from nothing. This is the philosophical and theoretical framework known as continuous creation, a concept that suggests the universe does not simply maintain itself through inertia or through the initial conditions set at the Big Bang, but instead requires constant renewal, constant reactualization by some creative force or principle at every infinitesimal instant. In this model, the past does not exist in any tangible sense. It has already ceased to be, and the future does not yet exist because it has not yet been created, leaving only the razor-thin boundary of the present moment as the sole locus of reality, a nopent that perpetually brings existence into being where there was previously nothing at all. The psychological appeal of this theory lies in its resonance with human experience. We live in what feels like an eternal present, continuously surprised by what emerges moment to moment, never able to step backward and verify that the past truly happened, never able to peer forward into what time will bring. The theory emerged most prominently in medieval and early modern theology, particularly in the work of philosophers and theologians who grappled with questions about God's relationship to creation, eventually gaining traction in 20th century physics and philosophy through the work of thinkers who questioned whether the past truly persists in any physical sense, or whether it is simply information preserved in the structure of the present moment. What makes continuous creation persist despite its conceptual challenges is precisely its capacity to sidestep certain paradoxes of causation and temporal ontology. If the universe is continuously created, then questions about what came before or what caused the initial creation become less pressing, and the need for an infinite regress of causes dissipates into the eternal creativity of the present itself. One of the most profound questions in modern physics asks whether the universe could have emerged from absolute nothingness, not from some pre-existing substance or cosmic seed, but from the absence of anything whatsoever. This concept challenges our deepest intuitions about causation and existence itself, Yet it has gained serious consideration among theoretical physicists and cosmologists who have spent decades wrestling with the mathematical implications of quantum mechanics and general relativity. The theory suggests that quantum fluctuations in a void state, governed by the uncertainty principle that permits brief violations of energy conservation at subatomic scales, could have spontaneously generated the entire cosmos, including space, time, matter, and energy as we observe them today. The mechanism works through the understanding that the total energy of the universe might actually be zero, with the positive energy of all matter and radiation precisely balanced by the negative energy of gravitational fields, creating a kind of cosmic ledger where everything sums to nothing. What makes this hypothesis intellectually compelling is that it requires no external creator, no pre-existing laws imposed from outside, and no mysterious force to initiate the event, as the laws of quantum mechanics themselves become the only requirement for spontaneous creation to occur. Yet despite its scientific legitimacy and mathematical coherence, we continue to find this idea almost psychologically unbearable, fundamentally resistant to the human mind's requirement for causes and explanations. Our cognitive architecture evolved to understand a world where things happen for reasons, where agents cause effects, and where something must come before something else, making the notion of uncaused emergence from genuine nothingness feel not merely counterintuitive, but almost morally wrong. At the heart of modern cosmology lies a paradox so profound that it challenges the very foundations of causality itself. The quantum creation event, the hypothesis that the universe emerged not from nothing, but from a quantum fluctuation in a pre-existing vacuum state. This theory proposes that the Big Bang was not an explosion occurring within space and time, but rather the spontaneous manifestation of space and time themselves, birthed from the probabilistic nature of quantum mechanics, operating at scales so infinitesimally small that the classical laws of physics dissolve entirely into mathematical abstraction. The mechanism underlying this idea rests on the observation that at quantum scales, particles constantly pop in and out of existence within what physicists call quantum foam, a seething backdrop of virtual particles that emerge and annihilate in fractions of a second, borrowing energy from the uncertainty principle itself in ways that do not violate the conservation of energy when averaged over appropriate time intervals. Applied to the universe's origin, this principle suggests that the cosmos could have spontaneously appeared through an identical process, except scaled to the grandest possible magnitude, where an entire four-dimensional spacetime manifold erupted into being from a quantum fluctuation in an undefined, pre-universal substrate, perhaps even from nothing at all in any meaningful sense. Yet this theory persists in serious scientific discourse despite its deeply counterintuitive implications, because it successfully addresses certain observational puzzles about cosmic inflation and the flatness of spacetime while remaining mathematically consistent within established quantum field theory. We have become so accustomed to this explanation that we rarely pause to contemplate the genuine strangeness of accepting that existence itself required no external cause, no creator, and no prior condition beyond the inherent probabilistic nature of quantum mechanics itself. In the standard model of cosmology, the universe began with the Big Bang, a moment of infinite density and temperature from which all space, time, and matter erupted into existence. Yet this singular moment remains deeply problematic for theoretical physics because the equations of general relativity break down at such extreme conditions, producing infinities that cannot be resolved and suggesting that our fundamental understanding of spacetime itself must be incomplete. Loop quantum cosmology emerges as a radical solution to this ancient puzzle, proposing that the Big Bang was not actually the beginning at all, but rather a quantum bounce, a moment of highest density from which the universe rebounded after contracting from a previous cosmic epoch, much like a ball falling and elastically bouncing back upward. This theory arises from the framework of loop quantum gravity, which attempts to reconcile quantum mechanics with Einstein's general relativity by quantizing spacetime itself into discrete, indivisible loops, suggesting that at the smallest scales, space is not smooth but granular, woven from tiny loops of geometry. In this framework, the universe cannot contract indefinitely because the quantum geometry prevents spacetime from becoming infinitely dense, establishing a maximum density threshold beyond which the contraction reverses into expansion, eliminating the troublesome singularity that has plagued cosmology for decades. The psychological appeal of this theory lies in its elegant resolution of a profound problem, offering a mechanism by which the infinities that plague classical cosmology are naturally tamed by quantum effects. Yet it simultaneously extends the universe's temporal history infinitely backward, replacing a singular creation moment with an eternal cycle of expansion and contraction. Imagine a universe so far in the future that time itself becomes meaningless, where entropy has reached its absolute maximum and all energy has dissipated into uniform nothingness. This is the Big Freeze, also called heat death, and it represents perhaps the most sobering cosmological endpoint ever conceived by modern physics. In this scenario, the universe continues to expand indefinitely, growing colder with each passing eon, until eventually all stars have burned out, all black holes have evaporated through Hawking radiation, and even the subatomic particles themselves have decayed into their most fundamental forms. What remains is a universe of infinite darkness and infinite cold, where no structure exists, no life can persist, and no consciousness could ever emerge to witness the silence. The temperature approaches absolute zero asymptotically, meaning it gets infinitely closer but never quite reaches it, creating an eternity of diminishing returns where virtually nothing ever happens again. The psychological mechanism that makes this theory persist is that it emerges naturally from our current understanding of thermodynamics and the accelerating expansion of the universe, making it feel less like speculation and more like inevitable mathematical consequence. We have normalized this grim endpoint because it aligns with established physics and observational evidence showing the universe expanding at an accelerating rate, driven by the mysterious dark energy that comprises most of the cosmos. Despite its deterministic sound, the Big Freeze remains one possibility among many, contingent upon assumptions about dark energy and the ultimate fate of matter that we cannot yet verify with certainty. Yet we discuss it with the confidence we might reserve for proven fact, allowing one possible future to calcify into expected destiny. Imagine the universe not ending in a bang or a whimper, but rather being consumed entirely, drawn down into an infinitely dense point like liquid spiraling into a cosmic drain. This is the essence of the Big Slurp theory, a speculative cosmological concept suggesting that the universe might be sucked into a microscopic wormhole or vacuum decay event, collapsing all matter, energy, and spacetime itself into a singularity from which no escape is possible. The mechanism behind this idea emerges from quantum field theory and our understanding of vacuum stability, where theoretically a false vacuum state could decay into a lower energy state, triggering a catastrophic phase transition that would propagate outward at the speed of light, fundamentally altering the properties of reality itself as it advances. In this scenario, everything we perceive, every star and galaxy and atom, would be pulled inexorably downward through increasingly severe gravitational gradients, until the entire cosmos vanishes into what would essentially be a black hole of incomprehensible proportions, leaving behind nothing but absolute emptiness where the universe once existed. The psychological grip of this theory persists despite its extremely low probability, largely because it represents a kind of cosmic horror that resonates deeply with human anxiety about inevitability and control, touching on our primal fear of being swallowed or consumed by something far greater than ourselves. We find ourselves drawn to contemplate such scenarios, even knowing they contradict current observations and mathematical models, perhaps because the Big Slurp embodies an ultimate surrender to forces beyond our comprehension, a finale so complete and total that it makes even heat death seem almost merciful by comparison. And in normalizing discussion of such apocalyptic possibilities, we somehow feel we have acknowledged and therefore negotiated with the darkness at the edges of existence. At the heart of every atom in your body, in every star scattered across the cosmos, and in the foundations of all matter as we understand it, exists a fundamental particle called the proton. For nearly a century, physicists have operated under the assumption that protons are essentially immortal, that they represent one of the few truly stable anchors in a universe characterized by constant decay and transformation. Yet emerging theoretical frameworks suggest something profoundly unsettling, that even protons might not be forever, that given enough time, an almost incomprehensibly vast span measured in trillions upon trillions of years, these building blocks of reality could spontaneously vanish, transforming into lighter particles like positrons and photons in a process known as proton decay. This phenomenon lies at the intersection of particle physics and cosmology, representing a challenge to our understanding of conservation laws and the ultimate fate of matter itself. According to various grand unified theories and supersymmetric models, proton decay should occur when quarks within the proton occasionally interact through mechanisms not yet directly observed in our laboratories. The predicted lifetime is so extraordinarily long, estimates range from 10 to the 34th power years or beyond, far exceeding the current age of the universe, that detecting even a single decay event requires monitoring thousands of tons of material in specially shielded underground facilities for extended periods. Experiments like Super Kamiokande have searched relentlessly for evidence of this decay, yet have found no definitive confirmation, which paradoxically strengthens constraints on which theoretical models might be correct. The concept persists in scientific discourse not because we have observed it, but because theoretical elegance and certain unified frameworks demand its existence as a consequence of deeper symmetries governing fundamental forces, creating a strange situation where we accept the reality of something we cannot yet prove happens at all. In 1974, Stephen Hawking proposed something that fundamentally challenged our understanding of black holes, those regions of spacetime where gravity becomes so intense that nothing, not even light, can escape once it crosses the event horizon. Hawking demonstrated through rigorous mathematical analysis that black holes are not entirely black, but rather emit radiation due to quantum effects occurring near the event horizon, where the fabric of spacetime itself becomes unstable and probabilistic. According to quantum field theory, virtual particle pairs spontaneously emerge from the vacuum of space constantly throughout the universe. And at the event horizon of a black hole, these pairs can become separated before they annihilate each other, with one particle falling into the black hole while the other escapes as radiation that appears to come from the black hole itself. This radiation carries energy away from the black hole, causing it to gradually lose mass over time in a process now known as Hawking radiation or black hole evaporation, meaning that even the most massive objects in the universe are not truly eternal, but are slowly consuming themselves from the inside out through quantum mechanical processes. The mechanism behind this phenomenon reveals a profound intersection between quantum mechanics and general relativity, two frameworks that usually operate at vastly different scales and have proven extraordinarily difficult to reconcile into a unified theory of quantum gravity. The smaller a black hole becomes, the hotter its Hawking radiation grows and the faster it evaporates, creating a runaway process where black holes ultimately vanish in increasingly intense bursts of energy, potentially ending not with infinite silence but with violent explosions. Imagine a universe billions of years in the future, long after the last stars have exhausted their nuclear fuel and collapsed into cold remnants scattered across an incomprehensibly vast darkness. This is the concept known as the Dark Era, a theoretical epoch extending trillions upon trillions of years into the cosmos's distant future, where the universe has become so cold, so sparse, and so profoundly isolated that the very fabric of existence seems to fade into meaningless void. During this period, the only remaining objects would be the decaying remnants of stellar death, black holes slowly evaporating through Hawking radiation, cold neutron stars radiating their final whispers of heat into absolute zero surroundings, and perhaps a few rogue planets wandering eternally through the black expanse, frozen and lifeless beyond any conceivable human comprehension. The mechanism driving this bleak vision emerges from our current understanding of thermodynamics and entropy, the fundamental principle that disorder in the universe constantly increases toward maximum chaos and equilibrium. As stars burn out and galaxies fall into darkness, protons themselves may theoretically decay over astronomical timescales, eventually breaking down into radiation and energy, leaving behind an utterly barren landscape devoid of any structure, complexity, or the chemical foundations upon which consciousness might arise. What makes this concept persistently haunting despite its purely speculative nature is how it confronts us with the ultimate fate of existence itself, forcing humanity to grapple with the possibility that given enough time, all meaning, all light, and all order dissolves into eternal, silent darkness. Yet paradoxically, this vision continues to captivate physicists and philosophers because it emerges logically from the most fundamental laws of nature we have discovered. Imagine the universe billions of years from now, long after the last star has exhausted its fuel and collapsed into darkness, long after black holes themselves have evaporated through Hawking radiation into the void, and what remains is something almost unimaginable, a cosmos of only elementary particles separated by vast distances, moving slowly through an infinite expanse of emptiness. This distant epoch is what physicists call the Degenerate Era, a theoretical phase of the universe that may stretch for quadrillions of years into the future, representing perhaps the most profound expression of entropy and cosmic decay ever conceived. During this incomprehensibly distant period, the only processes occurring would be the extraordinarily slow decay of protons themselves, which, while seemingly stable over human timescales and cosmic history thus far, may possess a finite lifetime measured in powers of 10 beyond human numerical comprehension. The mechanism driving this concept emerges from our deepest understanding of fundamental physics and the relentless march of the second law of thermodynamics, which dictates that all ordered systems must eventually dissolve into maximum disorder and that energy must always flow from concentrated states toward dispersal. As stellar remnants cool, as particles interact less and less, and as the universe expands ever faster, carrying matter and radiation further apart, the conditions necessary for any activity whatsoever vanish almost completely. What persists philosophically despite the sheer bleakness of this vision is that scientists continue to study and refine these models with genuine intellectual interest, treating the Degenerate Era not as a death sentence, but as a legitimate phase worthy of rigorous investigation and detailed theoretical analysis. In the unimaginably distant future, after countless trillions of years have passed, and the universe has entered what physicists call the Degenerate Era, there exists a hypothetical stellar remnant known as an iron star. This concept emerges from the understanding that even the most stable forms of matter, including the neutron stars and white dwarfs we observe today, are not truly eternal, for they too will eventually decay through a process so gradual that it defies human comprehension. An iron star represents what remains after proton decay has finally claimed every fundamental particle, leaving behind only iron nuclei, the most stable element in the universe, unable to fuse further or release energy through any known mechanism. The iron star exists in a state of absolute cold, its temperature indistinguishable from the background radiation of space itself, emitting no light, no heat, and no discernible radiation, existing as a relic of structure in an otherwise featureless cosmos. The mechanism that creates this theoretical future object lies in the fundamental instability of matter itself, for the very protons that compose atoms are believed by many physicists to be unstable over incomprehensibly long timescales, each one possessed of only a finite probability of decay, and given enough time, essentially infinite time, even this tiniest probability becomes certainty. What makes the iron star concept psychologically compelling is how it embodies the ultimate endpoint of thermodynamic degradation, the final conquest of entropy, where all complex structures have dissolved and even stellar remnants have surrendered to the arrow of time. We have normalized this vision of cosmic decline by incorporating it into our long-term models of universal evolution, treating the iron star future not as science fiction, but as a logical extrapolation of known physics principles, allowing us to contemplate with scientific authority a universe so aged and exhausted that consciousness itself becomes a distant memory of the distant past. In the incomprehensibly distant future, billions of years beyond the current age of the universe, the final stars will begin their inevitable decline toward extinction, marking not merely an astronomical transition, but a fundamental transformation in the nature of reality itself. Current astrophysical models suggest that stars, those brilliant furnaces of nuclear fusion that have powered the cosmos since the earliest moments after the Big Bang, cannot persist indefinitely. They will exhaust their fuel supplies over timescales so vast that human civilization seems to occur in a mere blink by comparison. And when these last stellar embers finally flicker into darkness, the universe will enter an era of cold, diffused twilight from which no new stars can ever be born. The mechanism behind this stellar mortality is rooted in the finite availability of hydrogen and helium that formed in the primordial universe, combined with the relentless thermodynamic principle that entropy always increases, ensuring that even the most efficient processes of nuclear fusion must eventually reach their conclusion, and that the universe's energy distribution will become increasingly uniform and unable to support the concentrated processes necessary for stellar ignition. Astrophysicists have calculated that the last stars, likely to be small red dwarfs with extraordinarily low mass and slow metabolic rates, could theoretically survive for trillions of years, far outlasting all more massive stars, and yet even these resilient cosmic embers will eventually cool and die, leaving behind a universe populated only by stellar remnants, rogue planets, and gradually cooling corpses of collapsed matter. Consider the possibility that time itself might not be a fundamental feature of reality at all, but rather an emergent property arising from the complex interactions of matter and energy within the universe. In timeless physics, sometimes called the block universe interpretation or eternalism, past, present, and future all exist simultaneously in a four-dimensional space-time continuum where time does not flow or progress in any meaningful way. This framework suggests that our subjective experience of moments passing, of causality unfolding, and of aging and decay are all illusions created by consciousness moving through a static geometric landscape that contains all of history at once. The psychological mechanism that keeps us anchored to conventional time consciousness, despite this possibility, is rooted in our evolutionary biology and perceptual limitations. Our brains developed to process information in a linear, sequential manner because survival required anticipating immediate threats and understanding cause and effect relationships within our local environment. This sequential processing creates an illusion of temporal flow, a sense that the present moment is somehow special or privileged compared to other moments, even though physics offers no mathematical reason why this should be true. We have normalized this perception so thoroughly that questioning the reality of time feels almost philosophically dangerous. Yet physicists like Einstein demonstrated mathematically that time and space are woven together in ways that make traditional notions of absolute time untenable. The theory persists in academic circles and continues to gain serious consideration because it resolves certain paradoxes in quantum mechanics and relativity, suggesting that rather than time being a mysterious substance in which events occur, time might simply be a dimension like the three spatial dimensions we navigate daily, with no preferred direction, no genuine flow, and no true distinction between past and future except in the observer's mind. One of the most perplexing paradoxes in modern physics and philosophy is what physicists call the problem of time, a fundamental mystery that suggests time itself may not exist as we intuitively perceive it, yet we organize our entire existence around its passage. When we observe the laws of physics at their most fundamental level, particularly in quantum mechanics and general relativity, we discover that the equations describing reality work equally well whether time moves forward or backward, a property known as time symmetry, and yet our everyday experience tells us that time has a distinct direction from past to future that causes precede effects, that we remember yesterday but not tomorrow. This disconnect between what the mathematics of the universe seems to be telling us and what consciousness experiences as the irreversible flow of moments creates what philosophers and physicists have struggled with for centuries. If the universe's deepest laws do not inherently contain a direction or arrow of time, then where does this arrow come from? And how can we be certain that time is anything more than a convenient construct our minds have imposed upon a fundamentally timeless reality? The mechanism underlying this problem stems from the observation that the fundamental equations of physics, from Newton's laws through Einstein's relativity to quantum field theory, are reversible, meaning that if you were to reverse the direction of every particle and force in the universe, the equations would still hold true. And yet thermodynamics, the study of heat and entropy, introduces an arrow pointing toward disorder and the degradation of energy, suggesting that time's direction comes not from the basic laws of physics, but from statistical probabilities and the tendency of complex systems to move toward states of maximum disorder. In the realm of theoretical physics, where the very fabric of spacetime bends under the weight of mathematical scrutiny, there exists an equation that attempts to do something almost unthinkable, to describe the quantum state of the entire universe itself. The Wheeler-DeWitt Equation, developed in the late 1960s by physicists John Wheeler and Bryce DeWitt, represents one of the most ambitious attempts to marry quantum mechanics with general relativity, creating a framework that could theoretically govern the universe at the moment of its birth. Unlike conventional quantum equations that describe particles evolving through time within a fixed spacetime background, the Wheeler-DeWitt equation operates under a radically different premise. It treats the universe as a closed quantum system where time itself is not a fundamental variable, but rather an emergent property that arises from the quantum state of all existence. This equation suggests that at the deepest level of reality, there is no absolute time ticking away in the background. Instead, there are only quantum states that contain all possible configurations of matter, energy, and geometry woven together in an eternal, unchanging mathematical structure. The psychological implication of this framework is profoundly disorienting, for it suggests that our intuitive understanding of causality, sequence, and temporal progression might be illusions generated by consciousness rather than fundamental features of reality. We perceive time as flowing inexorably from past to future, yet the Wheeler-DeWitt Equation whispers that this flow exists only in the eye of the observer, a useful fiction that our minds construct to navigate the quantum substrate beneath. The equation remains largely unresolved and deeply problematic, lacking clear predictions and struggling with fundamental interpretational issues. Yet the physics community continues to grapple with it, because ignoring it means abandoning the possibility of a truly unified theory of reality that encompasses both the infinitely large and infinitely small. In the pursuit of reconciling quantum mechanics with general relativity, physicists have arrived at a concept that fundamentally reimagines the fabric of spacetime itself, proposing that reality at its most fundamental level is not continuous, but rather discrete, composed of indivisible atoms of spacetime held together not by geometric structure, but by causal relationships alone. Causal set theory suggests that the universe is built from a vast collection of point events, each one connected to others through a partial ordering that respects causality, meaning that every event in existence can only influence those that lie in its causal future, creating a directed acyclic graph of all moments that have ever been or will ever be. Rather than thinking of spacetime as a smooth, infinitely divisible continuum as Einstein proposed, this theory posits that if you zoom down far enough, smaller than even the Planck length itself, you would discover that causality is primary and geometry is secondary, emerging only as an approximate large-scale description of the deeper causal structure underneath. The psychological appeal of this framework rests in its elegant simplicity and its radical departure from visual intuition. Instead of imagining spacetime as a four-dimensional rubber sheet that curves and bends, we must accept that at the deepest level, reality is fundamentally a web of causal connections, a vast partially ordered set where the only meaningful feature is which events can influence which other events, and this causal ordering automatically generates the appearance of space and time as statistical properties. What makes this theory particularly profound is that it suggests time itself is not a fundamental dimension, but rather an emergent phenomenon that arises from the causal structure, meaning that the arrow of time, the very sense that the past is fixed and the future is open, emerges naturally from the asymmetric nature of the causal relationships, with earlier events inevitably preceding later ones because the partial order demands it. One of the most provocative theories emerging from the intersection of quantum mechanics and general relativity proposes that time itself may not be fundamental to the universe, but rather an emergent property arising from quantum entanglement between distant parts of spacetime. According to this framework, originally developed through the work of theoretical physicists exploring holographic principles and quantum information theory, the very fabric of spacetime and the flow of temporal experience could be understood as a consequence of quantum correlations that bind the universe together at its deepest level. When two quantum particles become entangled, they maintain an instantaneous connection across space, sharing information in a way that classical physics cannot explain, and this phenomenon, when scaled up to cosmological proportions, may account for how different regions of the universe maintain causality and temporal coherence despite being separated by vast distances. The mechanism operates through a process of emergence, where time as we perceive it arises from the collective entanglement relationships woven throughout the quantum substrate of reality, much as classical physics emerges from the statistical behavior of countless quantum interactions at smaller scales. In this view, the arrow of time, the progression from past to future, would represent the increasing complexity and structure of entanglement patterns across the cosmos, with entropy increasing not as a separate phenomenon, but as a natural consequence of how entanglement grows and redistributes through expanding spacetime. This theory persists and continues to gain attention among theoretical physicists, despite remaining highly speculative and difficult to test empirically, largely because it offers a unified framework for understanding the relationship between quantum mechanics and gravity, two domains that have resisted unified description for decades, and because it suggests that temporal experience, far from being a mystical or purely subjective phenomenon, might be grounded in the most fundamental mathematical structures of physical reality itself. Within the foundations of quantum mechanics lies a profound puzzle that has troubled physicists for decades: the problem of time itself, which emerges not as a fundamental dimension but as something derived from the internal structure of quantum systems. The Page-Wootters Mechanism, proposed by physicist Don Page in 1983 and further developed by William Wooters, offers a radical solution to this conceptual crisis by suggesting that time is not an external parameter through which the universe evolves, but rather an emergent property arising from correlations between different parts of a quantum system. In this framework, the universe as a whole exists in a single, static, timeless quantum state called the universal wave function, containing no explicit temporal evolution whatsoever, yet within this frozen state lie hidden correlations and entanglements that serve as clocks and temporal records for observers within the system. When a subsystem becomes sufficiently entangled with another subsystem that we designate as a clock, the correlations between them create the illusion and subjective experience of time flowing forward through measurement and decoherence. The mechanism works through a subtle interplay of quantum entanglement and information, wherein the clock subsystem records information about the state of other subsystems, and these records become the basis upon which all observers measure chain and duration. What appears to be the passage of moments to conscious observers emerges naturally from this relational structure, with no need for an external, privileged time variable that evolution and causality might follow. This interpretation reconciles one of the deepest tensions in modern physics: the apparent incompatibility between the timeless nature of quantum mechanics and the manifest experience of temporal flow in our universe, by proposing that both perspectives are simultaneously true depending on which level of description one employs. In the depths of theoretical physics, where the fundamental nature of reality becomes increasingly abstract and counterintuitive, there exists a proposal that challenges our most basic understanding of what time actually is and how it emerges from the physical universe. The thermal time hypothesis, developed by physicist Carlo Rovelli and others working at the intersection of quantum mechanics and general relativity, suggests that time itself is not a fundamental feature of reality, but rather an emergent phenomenon that arises from the thermodynamic properties of physical systems. According to this hypothesis, what we experience as the flow of time, the distinction between past and future, and the very directionality of temporal progression are not built into the fabric of the universe at its deepest level, but instead emerge naturally from the way matter and energy become increasingly disordered and dispersed through space. The theory proposes that in a closed quantum system, the passage of time becomes defined by the growth of entropy, meaning that the arrow of time points in the direction of increasing disorder and thermodynamic imbalance. This radical reframing suggests that if we could somehow reverse entropy in a system, we would simultaneously reverse the direction of time itself, rendering the past and future interchangeable at the fundamental level. The implications are profound and unsettling because they imply that time is not something that flows independently through the universe, waiting for events to occur within it, but rather something that is generated by the very processes of energy dissipation and information dispersion that characterize physical systems. What persists in our collective understanding, despite this revolutionary perspective, is the intuitive sense that time is absolute, unchanging, and independent from the material world, a conviction so deeply embedded in human consciousness that even advanced scientific knowledge rarely dislodges it from our everyday experience and conceptualization of reality. When you examine the nature of time itself, you encounter one of philosophy's most intuitive yet paradoxical frameworks: presentism, the theory that only the present moment truly exists, while the past is gone and the future has not yet arrived. This concept emerges from our most immediate and visceral experience of reality, the undeniable sensation that we are living in a now that constantly moves forward, that the present instant is fundamentally real, while everything behind us has dissolved into memory and everything ahead remains uncertain and unmanifested. Presentism aligns perfectly with how we naturally perceive existence, for when you look around at this very moment, all you can ever directly experience is what is happening right now, and this creates a powerful psychological conviction that the present alone possesses genuine ontological status, that existence itself is somehow anchored exclusively to this fleeting instant we call the now. The mechanism underlying presentism draws from our embodied experience as conscious beings who encounter reality sequentially, moment by moment, unable to step outside the present to observe past or future directly. And this fundamental limitation of human perception becomes the foundation for an entire metaphysical worldview that treats the present as the only real temporal dimension. What makes presentism so persistent despite its logical vulnerabilities is precisely this alignment with consciousness itself, for our awareness seems to inhabit a perpetual present, and this felt experience carries enormous weight in how we conceptualize time's nature. Yet presentism faces formidable challenges, including the relativity of simultaneity in physics, which suggests that different observers in different reference frames cannot agree on which events are happening in the present moment simultaneously. And this scientific reality undermines the notion that there exists one objective, universal now that defines what is real. Eternalism proposes a radical reconceptualization of time itself, suggesting that past, present, and future exist simultaneously and equally in a four-dimensional block universe where all moments in time possess the same ontological status as the spatial dimensions we navigate daily. Under this framework, the distinction between what has already occurred, what is occurring now, and what will occur in the future represents merely our subjective perspective moving through a static landscape of events. Much like how an observer's position determines which portion of a landscape they perceive, yet the entire landscape exists independent of that observer's vantage point. The present moment, which feels so distinctly real and immediate in human consciousness, becomes understood not as a special metaphysical point where the future crystallizes into fact and the past becomes immutable, but rather as simply the location along the temporal dimension where our conscious experience happens to reside. Every event that has ever happened, from the formation of the first stars to conversations occurring in distant galaxies, and every event that will ever happen stretches out in temporal extension exactly as distant mountains stretch out in spatial extension, all equally real, all equally existing in the grand architecture of spacetime. This perspective emerges naturally from modern physics, particularly Einstein's theory of relativity, which demonstrates that time and space form an inseparable continuum, and that the concept of absolute simultaneity proves meaningless depending on one's reference frame. What makes eternalism particularly unsettling is how it collides with our deepest intuitions about free will, causality, and the flow of time itself. We experience a perpetual now that advances inexorably forward, yet eternalism suggests this experience represents a fundamental misunderstanding of reality's actual structure. Imagine time as a structure that is literally being constructed before your eyes, where the present moment represents the leading edge of an expanding block of reality that stretches backward through all of history, while the future remains entirely non-existent and unknowable. This is the essence of the growing block theory, a philosophical framework that attempts to reconcile our intuitive experience of time flowing forward with the apparent stubbornness of physical laws that seem indifferent to the direction of time. According to this model, only the past and present are real, possessing genuine existence and substantiality, while the future has no reality whatsoever until it arrives and is absorbed into the growing block of established fact. The present moment serves as the boundary layer where potential becomes actual, where quantum possibilities collapse into classical certainties, and where genuinely new events come into being rather than simply being revealed as already determined. This theory gains its appeal from how it validates our deepest intuitions about time, the sense that we are genuinely moving forward, that the past is fixed and unchangeable while the future remains open to possibility, and that there is something objectively special about the current moment that distinguishes it from all other moments. The psychological mechanism supporting this view rests on our fundamental experience of becoming, that persistent sensation that time carries us along a trajectory toward an unknowable tomorrow, that choices we make now actually matter because they determine what enters the growing block rather than merely expressing what was always destined. Yet the growing block theory persists despite considerable logical difficulties, for it struggles to explain what determines the speed of growth, why the block grows at all, or what any observer outside this expanding structure would measure, since general relativity suggests that simultaneity itself is relative and observer-dependent, making it unclear whose present moment counts as the true cutting edge of reality. Imagine standing at the edge of a black hole, watching your companion fall toward its event horizon while you remain safely at a distance. And as they descend deeper into that gravitational abyss, you observe something profoundly unsettling. Their movements begin to slow down, their clock ticks more gradually, and from your perspective, they appear to move in slow motion, as if the universe itself has decided to stretch time around them like taffy being pulled across the fabric of space-time. This is time dilation, one of the most counterintuitive consequences of Einstein's theory of general relativity, revealing that time is not the universal constant we once believed it to be, but rather a flexible dimension that bends, stretches, and compresses depending on gravity and velocity. The mechanism underlying this phenomenon emerges from the principle that the speed of light remains constant for all observers regardless of their reference frame, which necessitates that time itself must adjust to maintain this cosmic speed limit, meaning that in regions of intense gravitational fields or at velocities approaching light speed, time genuinely moves slower relative to observers in weaker gravitational fields or at rest. What makes time dilation particularly fascinating is that it operates simultaneously on two fronts. Gravitational time dilation, where massive objects literally warp spacetime and cause clocks to tick more slowly in their vicinity, and velocity-based time dilation, where objects moving at extreme speeds experience the compression of time compared to stationary observers. We have normalized this phenomenon despite its apparent violation of our intuitive understanding of reality by integrating it into the practical infrastructure of modern life, particularly in the precision requirements of global positioning satellite systems, which must account for the fact that their orbital clocks tick slightly faster than clocks on Earth's surface due to their reduced gravitational field and their orbital velocity, accounting for microsecond differences that would otherwise render navigation calculations meaningless within days. Imagine two lightning bolts striking at opposite ends of a railway platform at precisely the same instant, as observed by a stationary observer standing at the center point between them. Yet a passenger moving rapidly along the train perceives one bolt striking before the other, and neither observer is wrong according to the laws of physics, which reveals that the concept of simultaneous events existing across space depends entirely upon the reference frame from which those events are being measured. This phenomenon, known as the relativity of simultaneity, emerges directly from Einstein's special theory of relativity and fundamentally challenges our intuitive understanding that time flows uniformly and universally for all observers regardless of their motion through space. The mechanism underlying this counterintuitive reality stems from the constant velocity of light and the mathematical consequences of how time and space interrelate within different inertial reference frames, where an observer in motion relative to a particular location experiences time dilation and length contraction in ways that alter the temporal ordering of events separated in space. Meaning that two events which appear simultaneous to one observer will appear sequential to another observer moving at a different velocity, and the faster that relative motion, the greater the discrepancy in the perceived timing becomes. This is not merely a matter of perspective or measurement error, but rather a fundamental feature of the fabric of spacetime itself, where simultaneity is not an absolute property of events, but rather a relative quality that depends on the observer's state of motion. Consider the fundamental asymmetry that defines our experience of time. We remember the past with apparent clarity, yet the future remains entirely unknown to us. The past hypothesis, articulated most prominently by physicist Sean Carroll and building on earlier work by Ludwig Boltzmann, proposes a radical solution to one of cosmology's deepest puzzles, the arrow of time itself. This hypothesis posits that the universe began in an extraordinarily low entropy state at the moment of the Big Bang, and this initial condition is the ultimate explanation for why we observe time flowing in one direction rather than another. The mechanism underlying this observation relates to entropy and probability. As the universe evolves, it naturally tends toward higher entropy states because there are vastly more ways for a system to be disordered than ordered, making disorder statistically inevitable. However, this creates a profound mystery, because the laws of physics themselves are fundamentally time-symmetric, meaning they work equally well backward and forward through time, yet our universe displays this unmistakable directionality. The past hypothesis resolves this by asserting that the universe's low entropy boundary condition at its origin is simply a brute fact, an unexplained explainer that accounts for everything we observe about causality, memory, and the flow of time. We accept this asymmetry despite its seeming arbitrariness because without it, the very concept of cause and effect collapses entirely, along with our ability to remember anything or predict anything about future moments. The hypothesis persists in our understanding of cosmology not because it feels satisfying or because we have proven it true, but because it remains the most rigorous framework we possess for addressing why time moves forward rather than backward, and why the past appears fixed while the future remains open. The universe began in a state of extraordinarily low entropy, which remains one of the deepest puzzles in physics and cosmology. Entropy, fundamentally, measures disorder or the number of possible microscopic arrangements that correspond to a macroscopic state, and the second law of thermodynamics dictates that entropy always increases over time in closed systems. Yet our universe emerged from the Big Bang in an improbably ordered low-entropy condition, almost as though the initial conditions were fine-tuned with impossible precision. This seems to violate our intuitions about how systems naturally evolve, since random configurations almost always produce higher entropy states, not lower ones, which makes the cosmic beginning appear to require an explanation that transcends conventional thermodynamic reasoning. Physicists struggle with this asymmetry because the laws of physics work equally well in both temporal directions, yet the universe clearly possesses a temporal arrow that points from past to future, carried by the universal tendency toward disorder. The low entropy beginning suggests that something extraordinary occurred at the moment of cosmic origin, perhaps involving boundary conditions we cannot yet comprehend or physical principles that operated only at the absolute beginning. Some theorists propose that the initial singularity itself represents a unique state fundamentally exempt from entropy considerations, while others suggest that our universe might be one pocket in a larger multiverse where different regions began with different entropy values. The peculiarity deepens when we recognize that even a universe containing black holes, which represent maximum entropy objects, still possesses vastly less total entropy than it could possibly contain given its current size and energy content. We have normalized this paradox by treating it as merely another open question for future physics to resolve, yet it fundamentally challenges our understanding of causality and initial conditions themselves. Imagine standing at a mirror that reflects not your past, but the fundamental structure of time itself, and you begin to approach one of the most provocative ideas in theoretical cosmology known as the Janus Point. This concept, developed by physicist Julian Barbour and his collaborators, proposes that time does not flow uniformly in one direction from the Big Bang toward an infinite future, but rather that the universe possesses a temporal symmetry centered around a specific moment in cosmic history that functions as a kind of pivot point or turning axis. At this Janus point, the universe would reach its moment of maximum complexity and organization, after which the arrow of time would effectively reverse in a precise mirror image of how it began, creating a cosmos that unfolds identically in both temporal directions from this central fulcrum. The psychological appeal of this theory lies in its elegant resolution of one of physics' most profound mysteries, namely why entropy increases in one direction if the fundamental laws of physics are temporally symmetric, and it suggests that our experience of time flowing forward is not because time actually flows forward, but because we exist on the ascending side of this cosmic mountain, moving toward the peak. What makes the Janus Point particularly mind-bending is the suggestion that the universe possesses an inherent temporal symmetry that renders concepts like beginning and end somewhat illusory, since both directions from the central point would appear identical to observers within the system, meaning the Big Bang and the ultimate fate of the universe might not be truly distinct events, but rather two perspectives of the same cosmic mirror image. Imagine a universe where entropy reverses, where broken cups reassemble themselves on tables, where heat flows from cold objects to hot ones, and where the arrow of time points backward instead of forward into an increasingly disordered future. This concept, known as time running backwards or temporal reversal, represents one of the most philosophically disorienting ideas in physics and cosmology, challenging our fundamental understanding of causality, consciousness, and the nature of reality itself. At the heart of this theory lies a profound asymmetry in how we experience time compared to how the laws of physics actually operate. When physicists examine the fundamental equations that govern particle interactions and gravitational forces, they discover that most of these equations are time-symmetric, meaning that if you reverse the direction of time, the equations remain valid and describe perfectly plausible physical scenarios. Yet our lived experience tells us that time flows in only one direction, that causes precede effects, and that entropy always increases, creating an arrow of time that seems to pierce irreversibly from past toward future. The psychological mechanism underlying our fascination with backward time relates to our deep cognitive need for order and explanation. We have constructed an entire civilization around the assumption that yesterday has already happened and tomorrow has not yet occurred, that memories are of the past and anticipation belongs to the future. When we contemplate time running backward, we confront the vertigo of complete reversal where effects would precede causes, where we would remember the future and forget the past, where our consciousness itself would flow in an opposite direction through events. This thought experiment persists in theoretical physics and philosophical discourse, despite our inability to actually observe or demonstrate temporal reversal in the macroscopic universe, because it forces us to examine why time has a direction at all when the underlying laws seem indifferent to temporal orientation. Imagine standing at a fundamental crossroads of physics, where the very fabric of existence operates according to a principle so elegant that it suggests our universe might be fundamentally symmetrical in ways we have barely begun to comprehend. The CPT-Symmetry theorem, emerging from quantum field theory, proposes that the laws of physics remain invariant under three simultaneous transformations: charge conjugation, which reverses the electrical charge of particles; parity inversion, which mirrors spatial coordinates as though reflecting reality in a cosmic looking glass; and time reversal, which runs the arrow of causality backward. This mathematical framework reveals something profound about the nature of reality itself, suggesting that if you were to take any physical process, reverse every particle into its antiparticle, flip the spatial coordinates, and run time backward, you would still observe a process that obeys the fundamental laws of physics. The universe, in this conception, possesses a deep symmetry that transcends our ordinary perception of past and future, left and right, matter and antimatter. Some theoretical physicists have proposed that this CPT symmetry might extend to the cosmos as a whole, suggesting that the Big Bang and the ultimate fate of the universe could be mirror images of each other, separated by the arrow of time and entropy. This idea implies that the universe might not have a true beginning or ending in the conventional sense, but rather represents two temporally reversed halves of a single symmetrical whole, where what we perceive as the expansion following the Big Bang might be balanced by a mirror process occurring in the opposite temporal direction. Yet despite the mathematical elegance of this framework and its consistency with quantum field theory, we continue to observe phenomena that appear to violate CPT symmetry in subtle ways, or at least suggest that while the laws themselves may be CPT invariant, the actual state of the universe breaks this symmetry explicitly. One of the most perplexing mysteries in theoretical physics centers on a profound asymmetry in our universe. Matter vastly outnumbers antimatter, yet in the moments following the Big Bang, equal quantities of both should have been created according to our fundamental equations. This observation has led some cosmologists to propose a radical hypothesis that antimatter may have dominated entire regions of spacetime before the Big Bang itself, existing in whatever preconditions or prior states preceded our current cosmic epoch. The theory suggests that if we trace the universe backward through time, we might discover that antimatter held dominion in these ancient, inaccessible realms, and that our own matter-dominated universe represents only one chapter in a far grander cosmic narrative. This concept emerges from the desperate need to resolve what physicists call the baryon asymmetry problem, a fundamental imbalance that threatens the elegance of our mathematical descriptions of reality. The psychological appeal of this theory lies in its ability to transform an embarrassing contradiction into evidence of something deeper and more magnificent than we currently understand, converting a problem into a gateway to hidden dimensions of existence. We have become comfortable accepting this antimatter hypothesis despite its complete unfalsifiability, for there exists no conceivable experiment that could ever detect or verify conditions before the Big Bang, making it an article of faith rather than empirical science. Yet it persists within serious academic discourse precisely because it offers intellectual satisfaction, a narrative closure to our questions about cosmic origins, and the tantalizing suggestion that what we observe today represents merely the visible aftermath of an ancient, unreachable realm where opposite physical laws once reigned. Imagine if everything you know about time moves in the opposite direction in another version of reality, where entropy runs backward and causes flow forward into the past rather than the future, creating a universe that is fundamentally identical to ours in every physical law and constant, yet operating under a temporal symmetry so complete that it mirrors our own existence perfectly across an invisible cosmic membrane. This is the essence of the mirror universe theory, a concept that emerges from the deepest mathematics of physics and suggests that for every universe expanding forward through time with entropy increasing and disorder growing, there must exist a corresponding universe running in the exact opposite temporal direction, where the arrow of time points backward and all processes reverse themselves in perfect mathematical symmetry. The mechanism behind this theory rests on a profound asymmetry in our understanding of time itself, because while the fundamental laws of physics appear symmetric when examined mathematically, our universe exhibits a clear arrow pointing in one direction toward increasing entropy and disorder. Yet the mirror universe theory proposes that this asymmetry need not be universal, and that somewhere beyond our perception, another cosmos exists where low entropy states become the future and high entropy states become the past. What makes this theory particularly fascinating is how it reconciles thermodynamic arrow with fundamental physics, because if you reverse every particle's trajectory and reverse the direction of time itself, the mathematics of quantum mechanics and general relativity remain entirely intact and fully valid, suggesting that temporal direction might be less a fundamental property of reality and more an artifact of initial conditions and observer perspective. Consider the peculiar experience of time as it actually manifests in human consciousness, for we seem to exist within two fundamentally different temporal dimensions simultaneously, each operating according to its own logic and rhythm. The first dimension is what we might call chronological time, the objective progression of moments measured by clocks and calendars, the relentless forward march of seconds into minutes into hours, a one-directional arrow that physics describes as entropy increasing toward disorder. Yet alongside this mechanical dimension exists another form of time entirely, one we experience psychologically and emotionally, where moments of profound joy or suffering seem to stretch into eternities, while weeks of routine drift past in what feels like mere moments, where memories possess a weight and presence that sometimes overshadows the present instant, and where anticipation of future events can dominate our conscious awareness far more powerfully than the reality of what is actually occurring. This second dimension of time is deeply subjective, malleable, and responsive to our emotional and cognitive states, yet it is no less real in its effects upon our lives than the objective tick of the atomic clock. The mechanism underlying this phenomenon lies in how our brains process temporal information through multiple neural systems that operate at different speeds and scales, how attention acts as a lens focusing or diffusing our experience of duration, and how memory reconstitutes the past into narratives that feel alive and present within consciousness. We have normalized this strange duality so completely that we rarely acknowledge the fundamental paradox it presents, moving through our days simultaneously bound to objective time while swimming in subjective temporal experience, scheduling our lives by one standard while actually living by another. Assuming this split is simply how reality must be rather than a peculiar feature of conscious existence that demands deeper investigation into the very nature of temporal awareness itself. Imagine that at the most fundamental level of reality, the universe is not made of continuous matter or energy flowing through space, but rather of discrete packets of information processing themselves into existence, much like a vast cosmic computer running an unimaginably complex algorithm that generates space, time, particles, and consciousness itself as outputs of pure computation. This is the essence of digital physics, a theoretical framework that proposes the universe operates according to the principles of information theory and computation, rather than the classical laws of physics we have long assumed to be fundamental. Proponents of this view suggest that what we perceive as solid matter, electromagnetic radiation, and the fabric of spacetime itself are actually manifestations of information being processed at scales so minute that our instruments cannot yet detect them, and that the apparent randomness of quantum mechanics, the strange properties of dark matter and dark energy, and even the arrow of time itself might be explained if we understand reality as fundamentally computational in nature. The psychological appeal of this theory lies in how it transforms our deepest questions about existence into something that feels almost comprehensible through analogy to computers and algorithms we already understand, allowing us to imagine that beneath the mystery lies not magic but pure logic and information processing. Yet despite its intellectual elegance and its power to reframe ancient metaphysical questions in modern technological language, digital physics remains almost entirely speculative, lacking the observational evidence or mathematical framework necessary to elevate it from philosophical speculation to testable science, and we have somehow become accustomed to treating a hypothesis that fundamentally reimagines the nature of reality as merely one option among many competing theories. Equally worthy of serious consideration, despite its extraordinary claims and minimal empirical support. In the depths of theoretical physics, there exists a profound and unsettling proposition that challenges our most fundamental understanding of reality itself, one that suggests the universe is not made of matter or energy as we have long assumed, but rather of information, of pure bits of data, as if the cosmos itself were a vast computational structure operating at levels beyond our perception. This concept, articulated most famously by renowned physicist John Wheeler near the end of his illustrious career, proposes that every particle, every field, every force that comprises existence emerges not from some primordial substance, but from the binary distinctions that define information at its most basic level, the yes and no, the 0 and 1, the present and absent that form the building blocks of knowledge itself. The mechanism underlying this revolutionary idea rests on a deceptively simple observation, that whenever we observe or measure the universe, we extract information, we reduce quantum possibility into definite classical fact, and this act of information extraction seems to be fundamental to how reality crystallizes into being, as if the universe requires observation to transform from pure potential into concrete existence. Consider how deeply this inverts our intuition, how it suggests that matter is merely a manifestation of informational patterns, that what we call physical reality emerges from abstract computational structures that predate and supersede the very notion of substance itself. Yet despite the radical implications of this framework, despite the profound philosophical vertigo it induces when truly contemplated, the scientific community has largely incorporated this perspective as one valid among several competing frameworks, a testament to our peculiar modern capacity to accept that the deepest layer of reality might be mathematical, abstract, and fundamentally divorced from the tangible physical intuitions that guided us for millennia. Imagine that reality itself operates like the simplest possible computer program, where the entire cosmos evolves according to basic mathematical rules applied uniformly across a vast grid of discrete cells, each one containing only a finite number of possible states, and where the next state of every cell is determined exclusively by examining the current state of that cell and its immediate neighbors. This is the essence of the cellular automaton hypothesis, a theory suggesting that the universe might be fundamentally computational in nature, governed by local deterministic rules rather than the laws of physics as we understand them. In this framework, what we perceive as the flowing fabric of spacetime, the behavior of particles, and the emergence of complexity itself could all be explained through the iterative application of simple mathematical operations repeated across billions upon billions of these elementary cells, proceeding from one generation to the next in perfect synchronization. The theoretical appeal of such a model lies in its elegance and its ability to generate genuinely complex, seemingly random, and apparently irreversible phenomena from the simplest possible rule sets, as demonstrated by researchers studying systems like Conway's game of life. Yet our minds struggle to reconcile this reductive computational view with our direct experience of a universe that feels continuous, flowing, and governed by the smooth mathematics of calculus rather than discrete steps and local interactions. We have normalized the gap between these two frameworks by simply compartmentalizing them, accepting that at quantum scales the universe might be discrete, while maintaining our classical physics intuitions about larger phenomena, never fully confronting whether the entire cosmos might truly be nothing more than an elaborate algorithm unfolding deterministically in discrete time steps, or whether such a model could ever account for the apparent randomness and quantum indeterminacy that seems woven into reality's deepest fabric. Imagine a mathematical space so vast that it contains roughly 10 to the 500 possible universes, each with its own distinct set of physical laws and constants, and you begin to glimpse what theoretical physicists call the string theory landscape. This concept emerges from string theory, the ambitious framework suggesting that all fundamental particles and forces in existence are not point-like objects, but rather infinitesimal vibrating strings of energy, and the different ways these strings vibrate correspond to different particles and interactions. When physicists worked through the mathematics of how these strings could vibrate in higher dimensional spaces, they discovered that the equations permit an almost incomprehensibly large number of solutions, each solution representing a complete universe with its own dimensional structure, coupling constants, and particle physics. The fundamental mechanism at work here involves the compactification of extra dimensions, which means that the additional spatial dimensions required by string theory must curl up so tightly at scales far smaller than we can observe that we remain entirely unaware of them. And the precise geometry of how these dimensions fold determines the physical properties that would emerge in any resulting universe. What makes the landscape concept particularly mind-bending is how it transforms the question of why our universe has the specific constants and laws that permit our existence from a question requiring a unique answer into a question that no longer needs answering in the traditional sense. Because if infinite variations exist, we should naturally find ourselves in one of the rare configurations capable of supporting observers like ourselves. Within the theoretical frameworks of modern physics, pocket universes represent a fascinating extrapolation of inflationary cosmology, suggesting that our own universe may be merely one bubble among countless others, each with its own distinct physical laws, constants, and histories, separated not by distance in any conventional sense, but by barriers of spacetime so complete and impenetrable that they remain forever isolated from observation. The mechanism underlying this concept emerges from Alan Guthr's inflation theory, which proposed that the early universe expanded at incomprehensibly rapid rates. But this inflation did not necessarily occur uniformly or stop everywhere simultaneously, meaning that while expansion halted in some regions creating bubble universes like our own, the inflationary process could have continued eternally in other regions, endlessly spawning new pockets of spacetime with fresh initial conditions. What makes this theory particularly compelling is that it requires no exotic new physics beyond what current cosmological models already suggest, instead following naturally from quantum fluctuations during the inflationary epoch where minute variations in the expansion rate could cause certain regions to inflate more slowly while others continued at accelerated rates. Each pocket universe would exist in complete causal isolation from all others, meaning that not only could we never observe them, but no signals, information, or influence could ever travel between them, creating a multitude of separate realities with potentially wildly different properties where in some universes gravity might operate according to entirely different rules, where matter might never have condensed into stars, or where the fundamental forces carry strengths so divergent that chemistry and complexity as we understand them would be impossible. Consider the profound peculiarity of our existence itself. We find ourselves inhabiting a universe whose physical constants appear exquisitely calibrated to permit the emergence of conscious observers, yet we rarely stop to wonder whether this apparent design is evidence of intentional creation or merely a necessary consequence of our position as observers within a cosmos of infinite possibilities. The Anthropic Principle emerges from this observation and suggests that what we perceive as an improbably fine-tuned universe may not be improbable at all when we account for the simple fact that we could only ever observe a universe compatible with our own existence. In other words, we exist in a universe where the laws of physics permit life because we exist to observe it, and any universe incapable of producing observers would by definition contain no observers to remark upon its incompatibility with consciousness. This principle operates on a subtle but powerful logical mechanism. It recognizes that our sample size of universes is exactly one, and that universe has precisely the conditions necessary for us to be here asking questions about it. The stronger variant of the Anthropic Principle extends this reasoning to suggest that the existence of multiple universes, or a multiverse, would make our particular universe's fine-tuning entirely unremarkable, as there would inevitably exist innumerable universes with varying physical laws, and we naturally find ourselves in one of the rare versions that allows for biological life and conscious thought. Yet despite its logical elegance, the anthropic principle remains controversial within scientific discourse because it challenges the traditional aspiration of physics to explain phenomena through universal laws rather than through observer-dependent selection effects, and because it can sometimes function as a conversation stopper rather than a genuine explanation, allowing researchers to accept improbable coincidences without seeking deeper mechanical causes. Imagine a cosmic control panel with countless dials and switches, each one set to an extraordinarily precise value, and if even one of them were turned slightly in either direction, stars could never form, atoms could never exist, and life as we know it could never emerge from the void. This is the essence of the fine-tuning problem, a phenomenon that has captivated physicists and philosophers for decades as they contemplate the almost miraculous precision with which the fundamental constants of nature appear to be calibrated. The strength of gravity, the charge of the electron, the ratio of matter to energy in the universe, the expansion rate of space itself, and dozens of other fundamental parameters all seem to exist within vanishingly narrow ranges that permit the existence of complexity, consciousness, and observers like ourselves. Consider that if the strength of the strong nuclear force were even slightly weaker, protons and neutrons would never bind together to form nuclei, and chemistry itself would be impossible. Yet if it were even slightly stronger, all hydrogen would have fused into heavier elements in the first moments after the Big Bang, leaving no fuel for stars or water for life. The psychological and logical response to this observation has produced several competing interpretations of what this precision might mean. Some scientists have embraced the anthropic principle, reasoning that we can only observe a universe capable of producing observers, and therefore we should expect to find ourselves in a universe with these particular settings, regardless of how improbable they might seem from a detached perspective. Others have proposed that our universe is merely one among an incomprehensibly vast multiverse, where countless universes with different physical constants exist in parallel, and naturally we find ourselves in the one whose laws permit our existence. Yet despite these rational frameworks that attempt to explain away the fine-tuning as inevitable or unremarkable given appropriate context, the sense of profound improbability persists in the scientific and philosophical discourse. In the late 1990s, astronomers made a discovery that fundamentally challenged our understanding of cosmic destiny. The expansion of the universe is not slowing down as gravity would suggest, but accelerating at an ever-increasing rate. This acceleration is attributed to dark energy, a mysterious force that comprises approximately 68% of all matter and energy in the universe, yet remains almost entirely unknown to modern physics. The implications of this discovery lead to what cosmologists call the Big Rip scenario, a theory suggesting that dark energy will eventually become so dominant that it will overcome all fundamental forces, tearing apart galaxies, stars, and ultimately atoms themselves in an infinitely distant future. The psychological weight of this theory emerges from the profound uncertainty it represents. We have discovered that the majority component of our universe operates according to principles we cannot comprehend, and we have built mathematical models around this ignorance while acknowledging we are essentially working in the dark. The mechanism behind our acceptance of this doom-laden scenario stems from the remarkable success of the mathematical framework that predicts it, allowing scientists and the broader culture to accept accelerating cosmic annihilation as probable truth despite the absence of any deeper understanding of its cause. We have normalized the idea that the universe is driven by forces we cannot see, measure directly, or explain through established physics, and we have integrated this cosmic uncertainty into our cultural consciousness without significant existential crisis. The dark energy doom persists as a theoretical framework not because we truly understand it, but because we have learned to trust the mathematics, to accept mystery as a legitimate component of scientific knowledge, and to live alongside the notion that our universe contains fundamental secrets that may forever exceed human comprehension. Among the deepest mysteries confronting modern cosmology lies a phenomenon that astronomers and theoretical physicists call phantom dark energy, a hypothetical form of cosmic acceleration that behaves even more strangely than the dark energy already known to drive the universe's expansion. While conventional dark energy, represented by Einstein's cosmological constant, maintains a relatively stable density as the universe expands. Phantom dark energy would actually increase in density over time, growing more powerful and more dominant as cosmic expansion accelerates. This creates a theoretical scenario where the universe's fate becomes not merely endless but catastrophically violent, a future state where the very fabric of spacetime itself might eventually be torn apart in what physicists term the Big Rip, an apocalyptic event where galaxies, stars, planets, and ultimately atoms are systematically torn asunder by the relentlessly increasing force of this expanding energy field. The concept emerges from observations of the universe's acceleration rate and from certain interpretations of supernovae data that seem to suggest the acceleration itself might be increasing rather than remaining constant or decreasing. What makes phantom dark energy particularly unsettling is its violation of what physicists call the weak energy condition, a fundamental principle suggesting that energy densities should remain non-negative in any physically reasonable universe. Yet phantom dark energy would require a form of matter with negative pressure so extreme that it defies conventional understanding. Despite decades of refinement in observational astronomy, and despite increasingly sophisticated telescopic technology capable of measuring cosmic distances and velocities with remarkable precision, we still cannot definitively determine whether phantom dark energy truly exists, or whether our current models of cosmology are simply incomplete or misinterpreted. In the late 1990s, cosmologists faced a profound puzzle that threatened to unravel their understanding of the universe itself. Observations from distant supernovae suggested that the expansion of space was not slowing down as gravity should dictate, but rather accelerating at an increasing rate, as though some invisible force were pushing galaxies apart with ever greater vigor. To explain this unexpected phenomenon without abandoning Einstein's equations, physicists proposed the existence of a hypothetical form of energy permeating all of space, a concept they named quintessence, derived from the ancient Greek notion of a fifth fundamental element beyond earth, water, air, and fire. Unlike dark energy's uniform behavior, quintessence suggests a dynamic field with properties that vary across space and time, a kind of cosmic fluid whose density and pressure fluctuate in response to the universe's expansion, much like a quantum field that fills the vacuum of existence itself. The psychological appeal of quintessence lies in its explanatory elegance. Rather than introducing a cosmological constant that simply remains eternally mysterious, quintessence offers the tantalizing possibility that this accelerating force might have arisen from natural physical processes, from underlying laws yet to be discovered that would eventually make sense of what now seems paradoxical. We have come to accept quintessence despite the fact that it remains fundamentally undetected and unmeasurable by any instrument we possess, existing purely as a mathematical framework that fits observational data without revealing its true nature or composition. The theory persists in our scientific consciousness precisely because it acknowledges the limits of our knowledge while simultaneously suggesting that some unified principle awaits discovery, that the universe operates according to laws we have simply not yet comprehended, and that the acceleration of cosmic expansion, far from being an inexplicable anomaly, represents a window into deeper physics waiting patiently for human understanding to evolve sufficiently to perceive it. One of the most perplexing mysteries in modern physics involves a calculation that should work, but produces a result so absurdly wrong that physicists are left questioning the fundamental nature of reality itself. When scientists attempt to calculate the energy density of empty space, the vacuum energy that should arise from quantum field theory, their equations predict a value that is larger than observations allow by a factor of somewhere between 10 to the power of 120, a number so incomprehensibly vast that it defies human intuition and suggests something profoundly wrong with either our understanding of quantum mechanics or our understanding of gravity. This is the cosmological constant problem, perhaps the most severe discrepancy in all of theoretical physics, a gap between prediction and observation so enormous that if the universe actually behaved according to what the mathematics suggests, it would have torn itself apart in the first fractions of a second after the Big Bang, making stars, galaxies, planets, and life itself impossible. Yet here we are, observing a universe that clearly did not collapse or explode, a universe that apparently expanded at a relatively measured pace and allowed structures to form over billions of years. The psychological mechanism that keeps physicists working on this problem, despite its seemingly intractable nature, involves a kind of intellectual faith that the universe must make sense, that there exists some elegant resolution waiting to be discovered, some deeper principle or hidden symmetry that will eventually reconcile these wildly incompatible numbers and reveal why the vacuum energy contributes so little to the universe's expansion rate. We have normalized this crisis by converting it into a puzzle, by treating the unknowable gap as a problem to be solved rather than a sign that our entire framework might need reconstruction, continuing to search for supersymmetry or extra dimensions or quantum gravity effects that might suppress the vacuum energy's contribution, all while the fundamental question persists uneasily at the heart of modern cosmology. Imagine the universe not exploding into catastrophic destruction, not collapsing under its own weight, not being torn apart by dark energy in some violent cosmic rupture, but instead simply running out of fuel in the quietest possible way, fading into an infinite expanse of cold, empty darkness where nothing moves and nothing happens because there is fundamentally nothing left to move or happen at all. This is the concept known as the Big Whimper, a theoretical endpoint of cosmic evolution where the universe does not go out in a bang of apocalyptic violence, but rather in a whisper of thermodynamic exhaustion, where entropy has so thoroughly consumed all available energy that the very concept of change becomes meaningless. In this scenario, which emerges from our understanding of the second law of thermodynamics and the current observational data suggesting an accelerating expansion, the universe will eventually reach a state of maximum entropy, where all matter has decayed into its most stable forms, all stars have burned out, all black holes have evaporated through Hawking radiation, and the temperature of space itself asymptotically approaches absolute zero. What makes the Big Whimper psychologically distinct from other end-of-universe scenarios is its refusal to offer drama or closure. There is no moment of ending, only an infinite progression toward a state that is technically not an ending, but rather an eternal condition of absolute stillness and homogeneity. The mechanism driving this theory rests on established physics. The universe is expanding, entropy always increases in closed systems, and given enough time, every possible decay process will occur, leaving behind only photons so redshifted they carry virtually no energy, particles separated by distances so vast they will never interact again, and a void so absolute that the concept of time itself becomes philosophically questionable. The pre-Big Bang scenario represents one of the most intellectually audacious attempts to address what may be the deepest question in cosmology. What, if anything, existed before the moment we call the Big Bang? Traditional cosmology treats the Big Bang as an absolute beginning, a moment beyond which causality and time themselves cannot be extended. Yet this framework leaves us fundamentally unsatisfied because it appears to violate a basic principle of physics that every effect must have a cause. The pre-Big Bang model, most notably developed through string theory and loop quantum cosmology frameworks, proposes that our universe did not emerge from absolute nothingness, but rather from a prior state or even a prior universe that underwent a transformation so dramatic that it resembles a bounce or a bridge between two distinct cosmic epochs. In this conception, what we observe as the expansion of our universe following the initial singularity is actually the aftermath of an enormous quantum transition, where an earlier contracting or differently configured universe reached extreme densities and then transformed into what we experience as our expanding cosmos. The psychological mechanism underlying this theory stems from humanity's deep discomfort with genuine boundaries and ultimate beginnings, an intellectual anxiety that drives us to always seek what came before, to imagine that nothing truly begins from nothing. We normalize this framework by integrating it into mathematical structures that possess internal consistency and predictive power, allowing physicists to discuss pre-Big Bang conditions using equations and symmetries that feel scientifically legitimate even though they venture into territories where empirical verification remains profoundly elusive, creating a peculiar situation where our most rigorous mathematical tools extend our reasoning into domains that observation may never illuminate. String gas cosmology represents a radical reimagining of the universe's earliest moments by proposing that the primordial cosmos was not dominated by radiation or matter, but rather by a dense gas of fundamental strings existing at temperatures so extraordinarily high that spacetime itself existed in a fundamentally different state than we observe today. Rather than beginning with an infinitely hot singularity as traditional Big Bang theory suggests, String gas cosmology envisions the initial universe as a hot, dense medium in which countless vibrating strings jostled against one another in a pre-geometric phase where our familiar three spatial dimensions were curled up or compactified to minuscule scales, while other dimensions remained expanded. The mechanism underlying this theory emerges from string theory itself, which proposes that all fundamental particles are actually tiny vibrating strings, and at sufficiently high energies, the distinction between different particle types dissolves into pure string oscillations. In this primordial environment, strings would have interacted constantly through collisions and interactions that were governed not by the geometry of spacetime as we know it, but by the intrinsic properties of string theory itself, where spacetime geometry emerges only as a low-energy approximation. What makes string gas cosmology particularly intriguing is how it attempts to resolve some of the deepest problems in cosmology, including the horizon problem and the flatness problem that plague conventional inflation theory. By suggesting that dimensional transitions and string dynamics naturally explain cosmic properties we otherwise must artificially impose through ad hoc mechanisms like cosmic inflation. One of the most profound challenges to Einstein's foundational theory of relativity emerges from the possibility that the speed of light might not be constant across all times and places in the universe. While the constancy of light speed at approximately 300,000 kilometers per second has become the bedrock upon which modern physics is constructed, a growing body of theoretical work suggests that this fundamental constant may have actually varied throughout cosmic history. The varying speed of light theory, sometimes abbreviated as VSL, proposes that in the earliest moments after the Big Bang, light may have traveled at dramatically different velocities than it does today, potentially even infinitely fast in certain conditions. This concept emerged partly as an attempt to solve several persistent cosmological puzzles that inflation theory struggles to adequately explain, particularly the uniformity of the cosmic microwave background radiation and the apparent flatness of spacetime itself. The psychological mechanism underlying our resistance to this idea stems from our deep investment in Einstein's framework, which has proven so extraordinarily successful in predicting astronomical phenomena and enabling technologies that we have essentially granted it the status of unquestionable truth. We have normalized the constancy of the speed of light to such an extent that suggesting it might vary feels almost heretical within scientific communities, despite the fact that many aspects of physical reality have proven variable and context-dependent. Yet the theory persists in theoretical physics, continually re-emerging because it offers potential explanations for anomalies that fixed constants cannot resolve, suggesting that our attachment to unchanging fundamental principles may itself be a limitation we have accepted without sufficient justification, and that the universe's deepest secrets might require us to fundamentally reconsider what we consider truly constant and immutable across the vast expanse of spacetime. In the early 20th century, as astronomers peered deeper into the cosmos and observed that distant galaxies appeared to be moving away from us, physicists faced a profound mystery about the nature of the universe itself. The light arriving from these remote objects seemed systematically shifted toward the red end of the spectrum, a phenomenon known as redshift, which suggested that space itself might be expanding. However, Swiss astronomer Fritz Zwicky proposed an alternative explanation in 1929 that challenged this expanding universe model, suggesting instead that light itself might gradually lose energy as it traveled across the vast distances of space, much like a tired traveler growing weaker over an endless journey. According to this hypothesis, photons would slowly shed their energy through some unknown interaction with the cosmic medium, causing their wavelengths to stretch and appear redder to distant observers without requiring the universe to expand at all. The mechanism behind this tired light theory remained deliberately vague, as Zwicky and later proponents acknowledged that no known physical process could adequately explain such energy loss without violating fundamental principles of physics like energy conservation. Despite these conceptual difficulties, the theory persisted for decades, offering an intellectually simpler alternative to the counterintuitive notion that space itself was stretching and that the universe had a definable beginning and end. The tired light hypothesis allowed physicists to maintain a steady-state universe, infinite in time and space, which appealed to those uncomfortable with cosmic creation narratives. Yet observations of Type 1a supernovae, studies of galaxy evolution across different cosmic epochs, and precise measurements of the cosmic microwave background radiation eventually overwhelmed the tired light framework with evidence that the expanding universe model was correct. Plasma cosmology represents a radical departure from the standard Big Bang model of cosmic origins, proposing instead that the universe operates fundamentally through the electromagnetic interactions of ionized plasma rather than through gravity alone, and that the cosmos may have no beginning or end at all, but instead exists in a steady state of eternal transformation. This theory emerged primarily through the work of Swedish astrophysicist Hans Ulf Venn in the mid-20th century, who observed that plasma, the most abundant state of matter in the universe comprising stars, galaxies, and the space between them, possesses remarkable organizational properties when subjected to electromagnetic forces, and he theorized that these forces, not gravitational collapse, could explain the large-scale structure and evolution of the cosmos. In plasma cosmology, galaxies form and develop through the pinching effects of electric currents flowing through vast cosmic filaments, a mechanism known as the Z-pinch effect, which creates dense columns of matter without requiring invisible dark matter or dark energy to account for observed phenomena. The theory further suggests that what mainstream cosmology interprets as the expansion of space itself might instead represent the electromagnetic evolution of plasma structures, and that cosmic redshift could result from mechanisms other than the Doppler effect of receding galaxies. Despite offering elegant explanations for certain astronomical observations without invoking hypothetical substances or infinities, plasma cosmology has remained persistently marginalized within institutional science, existing primarily on the periphery of academic discourse even as its predictive power in some domains rivals or exceeds that of standard model cosmology. What if the universe did not begin in a state of infinite heat and density, but rather emerged from a condition of profound coldness and stillness, a primordial frost from which all motion and energy gradually awakened? The cold Big Bang theory proposes a radical departure from the standard hot Big Bang model by suggesting that the initial moments of cosmic existence were characterized not by explosive thermal intensity, but by a state approaching absolute zero, where quantum fluctuations were minimal and the fabric of spacetime itself existed in a kind of dormant, crystalline state. In this scenario, the universe would have begun as an almost perfectly ordered system, a kind of cosmic ice from which complexity and entropy would slowly emerge, rather than beginning in maximum chaos and cooling down over billions of years. Proponents of this concept point to certain interpretations of quantum mechanics and thermodynamic principles that suggest an initial state of minimal energy configuration might be mathematically consistent with observed cosmic phenomena, while offering potential explanations for why entropy appears to increase in one direction of time, and why the universe seems to possess such remarkably fine-tuned initial conditions. The mechanism underlying this theory rests on the notion that heat and motion might be secondary phenomena, emerging from an initially quiescent quantum substrate through processes we have yet to fully understand, rather than primordial features of existence. Despite possessing some mathematical elegance and offering novel perspectives on long-standing cosmological puzzles, the cold Big Bang remains far outside mainstream acceptance, largely because overwhelming observational evidence from cosmic microwave background radiation and the abundance of light elements overwhelmingly supports the hot Big Bang framework. Yet the theory persists in certain theoretical physics circles, suggesting a fundamental human inclination to question even our most well-established scientific foundations and to imagine fundamentally different origins for our reality. Shape dynamics represents a radical reimagining of fundamental physics that proposes the universe does not exist in a fixed background spacetime, but rather emerges entirely from the relational geometry of physical objects themselves. In this framework, developed by physicist Julian Barbour and others, there is no absolute space and no absolute time as independent containers within which events occur. Instead, space and time are secondary phenomena that arise from the comparative shapes and configurations of matter and energy throughout the cosmos. When we observe a distant galaxy moving away from us, or when we measure the expansion of space itself, we are not actually witnessing motion through a pre-existing void, but rather observing changes in the relative spatial relationships between massive structures that define geometry into existence through their mere configuration. The theory suggests that what we perceive as the arrow of time, the seemingly inevitable forward march from past to future, emerges from the statistical increase in the number of possible configurations available to matter as systems become more disordered and complex, a concept intimately tied to entropy and thermodynamic principles. This perspective eliminates the paradox of asking what lies outside the universe or what existed before the Big Bang, because both of these questions presume a background stage upon which reality performs. Yet if the stage itself is a construct of relationships rather than a fundamental substrate, such questions become logically meaningless. Shape dynamics challenges our most basic intuitions about existence and causality, suggesting that the universe may be fundamentally atemporal, with all moments equally real and existing simultaneously in a vast configuration space, and that our subjective experience of temporal flow is merely a localized phenomenon arising from our particular position within this landscape of possible arrangements. Consider the proposition that the universe itself might experience cyclical death and resurrection through a quantum mechanical process operating on the grandest possible scale, where the entire cosmos does not merely expand toward heat death or collapse into a singularity, but instead tunnels through the apparent barrier of entropy itself to emerge renewed in a state of lower complexity and higher potential energy, a phenomenon we might call quantum tunneling rebirth. In classical physics, the universe follows predictable paths governed by thermodynamic laws that suggest an irreversible march toward maximum entropy, a final state of uniform temperature and equilibrium where all useful energy has been exhausted and time itself becomes meaningless. Yet quantum mechanics introduces a peculiar loophole through the phenomenon of quantum tunneling, wherein particles can spontaneously appear on the opposite side of energy barriers that should theoretically be impassable, bypassing the classical laws that would otherwise confine them to their current state. Applied to cosmology, this theory proposes that the universe as a whole might behave as a quantum system operating on timescales of unimaginable magnitude, and that at the moment when entropy approaches its theoretical maximum and the cosmos faces true cessation, a quantum tunneling event could occur on a universal scale, allowing the entire system to tunnel through the barrier of entropy itself and emerge into a new configuration with reset conditions and renewed complexity. The psychological mechanism underlying this concept rests on our deep human resistance to permanence and absolute endings, our intuitive sense that destruction and creation are cyclical rather than linear, and our ability to extend mathematical models that work at subatomic scales upward toward cosmic significance. At the absolute bottom of existence, where temperature approaches absolute zero and quantum mechanics begins to dominate every interaction, physicists have discovered something profoundly unsettling. The vacuum is never truly empty. Even in the absence of all matter and energy, in the darkest void between particles, the quantum field underlying reality engages in what we call zero-point fluctuations, a ceaseless dance of virtual particles appearing and disappearing in timeframes so brief that they technically violate the conservation of energy. Yet they persist because the uncertainty principle allows them within the boundaries of mathematical permissibility. These fluctuations represent a fundamental restlessness inherent to the fabric of spacetime itself, a kind of cosmic tremor that cannot be eliminated or escaped, regardless of how much energy we remove from a system. The mechanism behind this phenomenon emerges from the wave nature of quantum fields, where uncertainty is not merely an epistemological limitation of our instruments, but an ontological feature of reality itself. Any quantum field must maintain a minimum energy state that is non-zero, and this ground state energy manifests as these microscopic, ephemeral particle pairs that blink in and out of existence, borrowing energy from the quantum vacuum in accordance with principles that seem to operate at the very threshold between something and nothing. In the heart of general relativity, one of physics' most profound mysteries emerges from the equations themselves. The existence of naked singularities, those catastrophic points where gravity becomes infinite and the very fabric of spacetime tears apart, exposed to the observable universe without the protective veil of an event horizon. The cosmic censorship conjecture, proposed by physicist Roger Penrose in 1969, suggests that nature fundamentally forbids such nakedness, that the universe possesses an inherent mechanism preventing these mathematical monsters from ever becoming physical reality. According to this principle, whenever gravitational collapse occurs, whenever a massive star dies and implodes under its own weight, a black hole forms with its event horizon sealing away the singularity inside, hiding it from external observers and preserving the predictability of physics itself. The mechanism operates as a kind of universal modesty, a fundamental law that shields us from encountering infinities that would make calculations impossible and render the future unknowable. Yet despite its intuitive appeal and mathematical elegance, cosmic censorship remains unproven, a conjecture rather than a theorem, supported by numerical simulations and physical intuition, but lacking rigorous mathematical demonstration. Physicists continue searching for both proof and counterexample, running increasingly sophisticated computer models to see if specific initial conditions might violate the principle, and remarkably, after decades of investigation, no violation has been discovered in any realistic scenario. The persistence of cosmic censorship as an unsolved problem reveals something profound about how science operates. We accept certain principles because they seem necessary for our theories to function, because they prevent absurdities, because the universe appears to respect them, yet we cannot fully explain why nature enforces them or whether they represent fundamental law or merely emergent consequences of deeper physics we have yet to discover. At the very heart of modern cosmology lies a concept that simultaneously represents our greatest achievement in understanding the universe and our most profound admission of failure. And that concept is known as the initial singularity, the hypothetical point in spacetime at which the universe is thought to have begun its existence approximately 13.8 billion years ago. The initial singularity is not merely a starting point in the conventional sense, but rather a boundary beyond which our current laws of physics cease to function and our mathematical descriptions break down into infinity, producing equations that yield nonsensical results and infinities that resist all attempts at meaningful interpretation. When we trace the history of the universe backward through time using general relativity, we discover that matter, energy, and spacetime itself become increasingly compressed and dense. And the further back we go, the more extreme these conditions become, until we reach a theoretical moment where the entire observable universe, containing all of its mass and energy, existed in an infinitely dense point of zero volume with infinite temperature and infinite curvature of spacetime. The psychological mechanism that allows us to accept this concept, despite its apparent impossibility, stems from a fundamental human need to identify origins and causes, a cognitive predisposition that drives us to seek the ultimate beginning, even when that beginning violates every principle of logic and observation we have developed. And we have become so accustomed to discussing the initial singularity as if it were a genuine physical entity that we rarely pause to acknowledge that we are essentially discussing a mathematical artifact rather than a real phenomenon. At the very beginning of our universe, so impossibly close to the moment of the Big Bang that it defies conventional measurement, exists a threshold of time so minuscule that it reshapes our entire understanding of reality itself. This is the Planck Epoch, a window of time lasting from 0 to approximately 10 to the negative 43 seconds after creation began, a duration so incomprehensibly brief that it makes a nanosecond seem like an eternity in comparison. Within this infinitesimal fragment of existence, the laws of physics as we know them completely break down and cease to function, creating a realm where quantum mechanics and general relativity collide head-on in a catastrophic collision of theories, neither able to describe what is actually happening in any meaningful way. During the Planck Epoch, the universe is believed to have been so dense, so hot, and so chaotic that gravity itself becomes quantized. Space and time are no longer smooth continua, but rather foam-like structures that bubble and fluctuate with quantum uncertainty, and every fundamental force of nature, including electromagnetism, the strong nuclear force, and the weak nuclear force, are theorized to have been unified into a single transcendent force of unimaginable power. Scientists recognize this as perhaps the most humbling frontier of physics because we cannot actually observe what happens here, we cannot test it in laboratories, we cannot probe it with any conceivable instrument, and our best mathematical tools simply yield infinities and nonsensical results when we try to apply them to these conditions. The Planck scale, named after physicist Max Planck, represents the fundamental unit of length and time itself, suggesting that below this scale, our very notions of space and time may not exist at all, or may be fundamentally different from anything our minds have evolved to comprehend. At the very beginning of time itself, in those first infinitesimal fractions of a second after the Big Bang, the observable universe was extraordinarily small and dense. Yet somehow it possessed regions that were causally disconnected from one another, meaning they could not have communicated with each other through any mechanism, not even light traveling at its maximum possible speed. The cosmic horizon problem emerges from this troubling observation. If different regions of the early universe were too far apart to have ever exchanged information or reached thermal equilibrium with one another, how could they possibly have ended up with the same temperature, the same density, and the same fundamental properties that we observe today when we look out at the cosmic microwave background radiation that fills all of space? The regions at opposite edges of our observable universe appear to be nearly identical in their physical characteristics, yet according to standard cosmological models, they should be completely independent and unrelated to one another. This mechanism operates through the expansion of space itself, which in the conventional Big Bang scenario was not rapid enough in the early moments to allow light signals to traverse the distances between distant regions before those regions separated beyond each other's cosmic horizons, the ultimate speed limit boundaries beyond which no causal influence can reach. The logical mechanism that drives this paradox stems from the finite speed of light combined with the vast distances involved and the age of the universe, creating a temporal constraint that seems to forbid the homogenization process that observation clearly demonstrates has occurred. Imagine a single particle floating in an infinite ocean of thermal energy, surrounded by countless other particles all moving in random directions at various speeds, colliding endlessly in a dance that appears chaotic yet follows perfect mathematical laws. This is the essence of the heat bath equilibrium concept, a theoretical framework that asks us to consider what happens when any isolated system reaches thermal equilibrium with its environment. The heat bath itself represents an infinitely large reservoir of energy at a constant temperature, so enormous and so well buffered that no matter how much energy a smaller system exchanges with it, the bath's temperature remains completely unchanged. When a cooler object is placed in contact with this theoretical heat bath, energy flows from the hotter reservoir into the cooler object until they reach the same temperature, at which point the microscopic dance of particle collisions reaches a state of statistical balance where as much energy flows one direction as flows in the other. This equilibrium state is not a frozen stillness, but rather a dynamic balance, a perpetual exchange that maintains perfect symmetry. The psychological mechanism that makes this concept so compelling is our intuitive understanding that disorder naturally increases, that systems left alone tend toward randomness. Yet this framework shows us that randomness itself has a structure, that even chaos follows predictable statistical patterns. We have come to accept this notion so thoroughly that it underlies nearly all modern thermodynamics and statistical mechanics, yet we rarely pause to consider the profound strangeness embedded within it. The heat bath equilibrium assumes an infinitely large environment, an assumption we know is impossible in our finite universe. Yet we apply this framework constantly to real systems with apparent success, treating finite thermal reservoirs as infinite when they are large enough relative to the objects we study. At the furthest reaches of cosmological speculation lies a concept so counterintuitive to modern physics that it challenges the very foundation of how we understand temporal reality itself. The infinite static universe theory proposes that time does not actually flow or progress as we subjectively experience it, but rather that all moments, past, present, and future, exist simultaneously in a vast, unchanging four-dimensional block, with consciousness moving through this predetermined structure like a needle tracing an already written record. In this framework, the Big Bang and the heat death of the universe are not actual events separated by billions of years of dynamic change, but rather fixed boundary conditions of an eternal crystalline structure where every atom, every particle, and every conscious thought exists eternally in its designated spacetime coordinate, neither created nor destroyed, merely arranged in the grand architecture of existence. The theory suggests that what we perceive as causality and time's arrow are merely cognitive illusions generated by our limited perspective as we traverse this static manifold. Our memories of the past and anticipations of the future nothing more than neural correlates of our position within a four-dimensional structure that has always been complete and whole. This perspective emerges from taking seriously the mathematical frameworks of relativity theory, which already treat time as a dimension rather than a flowing medium, yet we persistently cling to the intuitive notion that reality unfolds and becomes, that novelty emerges, that choices matter because futures remain open. The persistence of our temporal intuitions, despite theoretical considerations pointing toward eternalism, reveals a profound disconnect between intellectual understanding and embodied experience, suggesting that our minds may be fundamentally incapable of genuinely grasping a universe where nothing truly happens, where all is eternally fixed in place, and where the sensation of moving through time represents merely our consciousness navigating a landscape that transcends becoming altogether.